What if I told you that the most mind-bending, reality-defying events in the universe aren't happening in the hearts of blazing stars or swirling black holes, but in places so cold that reality itself seems to unravel? Picture a cold beyond anything we experience on Earth, a deep, cosmic chill where atoms slow to a near standstill and temperatures approach the ultimate limit of cold, absolute zero. Out there, in the vast and silent expanses between the stars, lie regions like the Boomerang Nebula and dark molecular clouds, where the very fabric of physics behaves in ways that challenge our understanding of existence itself. These are not empty, lifeless voids, far from it. They're cosmic laboratories, natural arenas where matter and energy interact under conditions so extreme that we can barely replicate them even in our most advanced labs. In these frigid realms, quantum phenomena emerge on a grand scale, strange chemistries brew the building blocks of life, and stars are born from the very darkness that seems to swallow all light. It's here, in the deepest cold, that the universe conducts its most mysterious experiments, showing us just how little we truly know, and just how much wonder remains to be discovered. In this video, we're setting out on a journey to the coldest corners of the cosmos. We'll explore why these extreme environments become hotbeds of bizarre activity, from ghostly nebulae that defy explanation to the birth cries of new solar systems echoing across light years of frozen space. You'll see how the rules you thought were fixed begin to bend and twist, inviting us into a richer, stranger, and more magnificent vision of reality. So settle in, open your mind, and get ready to explore the beautiful, bewildering, and profoundly mysterious worlds that await us in the deep freeze of space. But to truly grasp the sheer strangeness at play in these cosmic deep freezes, we first need to redefine our very idea of cold. When we say it's cold outside on Earth, we're speaking in relative terms. A bitter winter day might be minus 20 degrees Celsius, and even the most extreme places on our planet, like the high ridge of the East Antarctic Plateau, might scrape down to around minus 98. That's undeniably frigid for us, but in the grand scheme of the universe, it's practically balmy. The cold we're talking about in space operates on a completely different scale. A scale that begins at a point called absolute zero. This isn't just another number on a thermometer, it's the fundamental baseline of coldness in our universe, the temperature at which all classical molecular motion theoretically comes to a complete and utter stop. That point is minus 273.15 degrees Celsius. Now, space itself never quite reaches this perfect stillness. There's always some residual energy, some whisper of heat, but many regions come heart-stoppingly close. The Boomerang Nebula, for instance, drifts at a mere 1 degree above this ultimate limit. At these temperatures, matter doesn't just get sluggish. It starts to behave in ways that seem to defy the very logic of our everyday experience. The normal, bumping, jostling dance of atoms slows to a near standstill. This profound stillness is the key that unlocks the door to the bizarre. Without the constant thermal noise that dominates warmer environments, more subtle and exotic forces come to the forefront. Quantum mechanical effects, which are usually drowned out at higher temperatures, suddenly become the dominant players on a macroscopic stage. This is where we encounter the truly exotic states of matter that sound like science fiction. Superfluids that can flow without any friction and climb the walls of their containers, or superconductors that can carry electrical currents indefinitely without losing any energy. These phenomena aren't just laboratory curiosities, they are the direct results of matter being pushed to its ultimate cold extreme. So, when we look out into these dark, seemingly empty regions of space, we're not looking at a void. We're looking at a pristine, ultra-cold laboratory, a natural experiment set up by the universe itself. It's an environment of such extreme order and minimal energy that the smallest interactions become magnified. The most delicate quantum processes can play out, and the rules of reality as we know them begin to bend. This fundamental shift in how matter and energy interact is precisely why the coldest places become such incredible hotbeds of strange and wonderful activity. Absolute zero represents far more than the bottom of the temperature scale. It is a profound frontier where the predictable universe we know gives way to a realm governed by entirely different rules. At this theoretical limit of -273.15 degrees Celsius, the ceaseless jostling of atoms and molecules grinds to the absolute minimum, a state of near-perfect order. This isn't just about things getting slower or colder. It's about a fundamental shift in the very behavior of matter and energy. The familiar laws of classical physics, which describe the motion of planets and the trajectory of a thrown ball, begin to falter and fade. In their place, the bizarre and counterintuitive principles of quantum mechanics rise to dominate. At these extremes, concepts we take for granted, like a fluid's resistance to flow or a material's opposition to electrical current, simply vanish. This is where we encounter phenomena that sound like they're pulled from a fantasy novel. Superconductivity emerges, a state where electrical current can zip through a material with zero resistance, never losing energy to heat, potentially enabling technologies like flawlessly efficient power grids or levitating trains. Then there's superfluidity, an even stranger state where a liquid like helium loses all viscosity. It can flow uphill, seep through impossibly tiny pores that would contain any normal substance, and even create a perpetual fountain that never stops. These aren't just laboratory tricks, they are direct manifestations of quantum behavior playing out on a scale we can actually see and measure. They occur because at such profound cold, individual atoms lose their distinct identities and begin to act as a single, coordinated quantum wave, a collective entity operating in perfect, eerie harmony. The incredible thing is that nature has already created environments where these exotic states can form naturally. The Boomerang Nebula, for instance, is a cosmic example of this extreme physics in action. Its expanding gases have created conditions just 1 single degree above absolute zero, making it the coldest known natural place in the entire universe. Out there, in that silent, frigid expanse, the same quantum rules that we struggle to create in highly controlled labs on Earth are simply the default state of being. This provides astronomers with a priceless natural laboratory. By studying the light and the behavior of matter in such a nebula, we can observe how quantum effects influence the formation of cosmic structures, the scattering of starlight, and the very life cycle of stars themselves. This transition from the ordered stillness of extreme cold to the vibrant, probabilistic chaos of the quantum world is the core reason these cosmic iceboxes become such active hubs for the strange and unexpected. The absence of thermal noise acts like a blanket of silence, allowing the faintest whispers of quantum phenomena to be heard loud and clear. It hints that the universe operates on a set of deeper, more fundamental laws that only reveal themselves under the most extreme conditions. The cold, therefore, isn't an end but a beginning, a gateway to a hidden layer of reality where our conventional understanding breaks down and a new, more wondrous physics awaits our discovery. Now, to truly appreciate the role of cold as a cosmic architect of the bizarre, we must venture into one of its most enigmatic and productive creations, the dark molecular cloud. Picture a vast, swirling tapestry of gas and dust so dense that it blots out the light of the stars behind it, appearing as a stark, black silhouette against the glowing backdrop of the Milky Way. Within these colossal cosmic nurseries, temperatures routinely plummet to a mere 10 degrees above absolute zero. At first glance, such a place seems like the epitome of stillness and silence, a frozen vault where nothing should ever happen. But that impression couldn't be more wrong. This profound cold is not a death sentence for chemistry. It is its greatest and most precise enabler. The secret lies in the unique conditions this deep freeze creates. The crushing density of these clouds acts as a perfect shield, protecting their inner sanctums from the harsh, high-energy radiation that floods interstellar space. This protection is absolutely vital. Out in the open, a newly formed molecule would likely be almost instantly blasted apart by a stray ultraviolet photon. But inside the cloud, in that deep, dark, cold quiet, molecules are given the precious gift of time. Chemical reactions, which in warmer environments would be a frantic, chaotic scramble, can here unfold with a slow, deliberate, almost meditative precision. Atoms and simple molecules, frozen onto the surfaces of microscopic dust grains like frost on a window pane, have the opportunity to meet, to stick, and to gradually build themselves into something far more complex. This is how the universe's most intricate chemistry begins, not in a blaze of heat, but in the profound patience of cold, and the results are astonishing. Using powerful radio telescopes that can peer through the darkness and detect the unique signatures of molecules vibrating in the cold, astronomers have compiled an inventory that reads like a mad chemist's shopping list. They've found simple things like carbon monoxide and water ice, but also far more complex organic molecules. They've even identified ethyl formate, the very same compound that gives raspberries their distinctive scent and rum its characteristic aroma. Imagine that, a vast frozen cloud in the emptiness of space, subtly smelling of fruity rum. It's a delightful and profoundly strange thought, but the implications are far greater than just cosmic perfumery. These detections are a powerful clue that the fundamental building blocks of life, the complex organic molecules like amino acids and sugars, are not rare accidents but could be a common product of the galaxy's coldest places. These dark clouds are essentially vast, frozen factories, quietly and methodically assembling the very ingredients that, when delivered to a young, warm planet by comets or asteroids, could provide the raw material for life to begin. The cold, therefore, is not a barren wasteland. It is a protective cradle, a nurturing ground where the delicate and complex chemistry of the cosmos can proceed without interruption, hidden within the darkness and waiting for its moment to seed new worlds with potential. And to see this principle in its most spectacular form, we need look no further than the Boomerang Nebula, a cosmic masterpiece of cold that holds the uncontested title of the coldest natural place we have ever discovered. Located some 5,000 light-years from Earth, this preplanetary nebula is the final, breathtaking performance of a dying star, a sun-like star in its last agonizing throes. As it sheds its outer layers, it isn't simply releasing a gentle puff of gas. It's firing a supersonic jet of material into the void at speeds approaching 160,000 kilometers per hour. This is where the magic of physics takes over. As this gas expands into the near-perfect vacuum of space, it undergoes a process called adiabatic cooling. Think of it like the universe's most powerful air conditioner. Just as you feel a can of compressed air get intensely cold when you spray it because the expanding gas inside draws heat away from the can, the rapidly expanding gas of the Boomerang Nebula cools itself to an almost unimaginable degree. This is how it achieves its record-breaking temperature of a mere 1 degree above absolute zero. It is, quite literally, colder than the faint afterglow of the Big Bang itself that permeates all of space. This profound cold dictates every aspect of the nebula's bizarre and beautiful appearance. The outflowing gas is mixed with fine dust grains, and in this ultra-cold environment, they interact with starlight in a unique way. The light from the central star scatters off these dust particles, creating the nebula's iconic, asymmetrical bow tie shape that earned it its name. But this isn't just a static sculpture, it's a dynamic and evolving physical laboratory. At these temperatures, the very properties of the gas and dust are alien. Molecular motions are so sluggish that chemical reactions proceed at a glacial pace, and the behavior of matter is governed more by quantum rules than classical ones. Astronomers study the light that filters through and reflects off this frigid outflow to understand the composition and physics at work, gleaning insights that are impossible to replicate in any lab on Earth. What makes the boomerang so crucial to our understanding is that it captures a fleeting cosmic moment. It represents a brief phase in a star's life, a bridge between the death of a red giant and its rebirth as a glowing white dwarf surrounded by a radiant planetary nebula. By studying this extreme environment, we learn how the raw materials of stars are recycled back into the interstellar medium, but now enriched with new elements and forged in conditions of unimaginable cold. This process seeds the galaxy with cold, complex molecules and dust, the very stuff that will one day collapse to form new stars, planets, and perhaps even life. The Boomerang Nebula, therefore, is far more than a celestial curiosity. It is a vital key to understanding the life cycle of matter in the cosmos, demonstrating how the cold vacuum of space can become a crucible for both destruction and creation, intimately linking the death of one star to the potential birth of futures yet to come. And it is within these unimaginably cold environments that we witness one of the most profound shifts in the behavior of reality itself. The moment the familiar world of classical physics fades away and the bizarre, counterintuitive realm of quantum mechanics takes center stage. This transition isn't a subtle one. It's a complete overhaul of the rules. At the temperatures we find in places like the heart of a dark molecular cloud or the expanding gases of the Boomerang Nebula, the constant thermal jostling that usually masks these quantum effects is almost entirely silenced. It's like the universe has turned down the volume on everything else, allowing us to hear the faint, whispering symphony of quantum behavior playing out on a grand, cosmic scale. One of the most spectacular examples of this is a state of matter known as a Bose-Einstein condensate. In our everyday world, we're used to particles behaving as distinct, separate objects. But when matter is cooled to within a fraction of a degree above absolute zero, something incredible happens. Countless individual particles, bosons to be precise, lose their individual identities entirely. They stop acting like a crowd of separate entities and instead merge into a single, unified quantum object, a kind of super atom that behaves as one. This isn't just a theoretical idea. We've created Bose-Einstein condensates in laboratories on Earth, and they exhibit properties that seem to defy logic. But the truly mind-bending concept is that nature might be creating these condensates on a vastly larger scale out in the depths of space, within the immense, cold interiors of certain nebulae, or even in the mysterious halos of dark matter. Conditions could be just right for these macroscopic quantum states to form naturally. This means that a cloud of gas light years across could, in a very real sense, be acting as a single quantum entity, a notion that stretches our understanding of reality to its breaking point. This leads us directly to another quantum oddity that might be thriving in these cosmic deep freezes, superfluidity. We're familiar with liquids having viscosity, a kind of internal friction that makes honey pour slowly and water form droplets. But in a superfluid, that friction vanishes completely. The liquid can flow without any loss of energy. It can creep up the sides of a container and over the top, and it will never, ever swirl into a vortex that slows down. On Earth, we see this with liquid helium when it's cooled to just a few degrees above absolute zero. Now, imagine that same property applied to the components of a neutron star. These incredibly dense, city-sized remnants of supernova explosions are thought to have interiors where neutrons, freed from the constraints of heat, form a superfluid sea. This could explain sudden starquakes or rotational glitches observed in pulsars. The entire crust of the star might be shifting over a frictionless, superfluid core. Even within the vast, cold reservoirs of interstellar gas clouds, pockets of superfluid matter could exist, allowing energy and momentum to be transferred with impossible efficiency, completely altering how we think these clouds collapse to form new stars. These quantum phenomena are far more than just cosmic curiosities. They are active, driving forces behind the strange activity we observe. The bizarre behavior of matter at these temperatures directly influences the process of star formation. In a cold molecular cloud on the verge of collapse, the presence of quantum effects like superfluidity or macroscopic coherence could determine how efficiently the cloud fragments, how much mass a nascent protostar can gather, and even the ultimate fate of the resulting solar system. It means that the birth of a star isn't just a story of gravity versus pressure. It's a story deeply intertwined with the probabilistic, wave-like nature of reality that only reveals itself in the deepest cold. This reveals a universe that isn't just governed by the certain, predictable motions of billiard ball atoms, but one that operates on a fundamental level of probability and interconnected waves, a hidden layer of physics that only becomes apparent when the heat of creation finally dies down. This profound cold, which seems so hostile to activity, is in fact the essential ingredient for the most fundamental act of cosmic creation, the birth of a star. It's a beautiful paradox. The very thing that brings molecular motion to a near standstill is what allows gravity to perform its grandest work. Within the deep, dark hearts of these molecular clouds, immense pockets of gas and dust begin a slow, inexorable dance, pulled together by their own mutual attraction. Now, you might think that such extreme cold would freeze this process solid, locking everything in a static, icy grip, but the opposite is true. In the warmer environments we're used to, thermal pressure acts like a powerful outward force, with fast-moving atoms and molecules constantly pushing against each other and resisting collapse. It's a form of energetic opposition to gravity's pull, but in these cosmic nurseries, the cold removes that opposition. With thermal pressure dialed down to almost nothing by the near absolute zero temperatures, gravity faces far less resistance. It can gently and steadily draw material inward, allowing vast, diffuse clouds measuring light years across to gradually condense into denser knots and cores. These are the seeds of future stars, known as protostars. They are cradled in the dark, drawing in more and more material from their surroundings, growing in mass and density until the pressures and temperatures at their cores become so immense that they ignite the fires of nuclear fusion, and a new star officially joins the cosmos. Yet this elegant, seemingly straightforward process is anything but simple. The journey from a cold, quiet cloud to a brilliant, blazing star is a cosmic obstacle course, a delicate balancing act between competing forces that is still not fully understood. While gravity is the great architect, magnetic fields are the invisible scaffolders within these clouds. These fields, woven through the gas and dust, can provide a supporting structure that actually holds a cloud up against the relentless pull of gravity, effectively putting star formation on pause. For a collapse to proceed, this magnetic support must somehow be dissipated, often through a slow, complex process called ambipolar diffusion, where neutral particles gradually slip past the ionized particles locked to the magnetic field lines. Adding to this complexity is the role of supersonic turbulence. These clouds are not serene and placid. They are churning and chaotic, with internal motions that can sometimes tear a collapsing core apart before it has a chance to form a star, while at other times, the shock waves from that same turbulence can actually compress gas and trigger the collapse in the first place. It's a dynamic and unpredictable environment where creation and destruction dance a delicate tango, and we mustn't forget the chemistry. We just explored the complex molecules forming on icy dust grains. These molecules, particularly carbon monoxide, are brilliant at radiating away any tiny amounts of heat that are generated during the early stages of collapse. This efficient cooling is vital. It keeps the cloud cold and prevents a buildup of thermal pressure that could otherwise halt the entire process. The result of this intricate interplay is a nursery that is far from a featureless blob of gas. The marriage of cold and gravity, moderated by magnetism and turbulence, sculpts the cloud into stunning and strange structures. Giant, intricate filaments of denser gas stretch across light years of space, like cosmic rivers flowing into hubs of intense activity. And from the deep within these hubs, as a protostar begins to spin and accumulate mass, it often launches powerful, focused jets of material screaming outward at nearly the speed of light. These bipolar outflows carving through the surrounding cloud are a star's birth cry, a necessary release of angular momentum that allows the infant star to continue gathering mass. So, within these freezing, seemingly dormant vaults, we find not stillness, but a frenzy of creative activity, a testament to the universe's ability to build its most magnificent structures from the deepest cold. But for all the grandeur of star formation, some of the most profound and delicate work in these cold regions happens on a scale almost too small to comprehend, centered on the most humble of cosmic materials, dust and ice. We often think of the void between stars as just that empty space, but it's far from it. It's filled with a fine, microscopic haze of silicate and carbon-rich dust grains, the ashes of long-dead stars. And in the deep cold of molecular clouds or the outer reaches of forming solar systems, these tiny particles become something extraordinary. They act as miniature cryogenic laboratories, their surfaces providing a solid anchor where wandering atoms, moving sluggishly in the frigid temperatures, can finally meet, stick, and react. Without these dust grains, many of the universe's most important molecules might never form. The chance of two atoms finding each other and bonding in the vast emptiness of a gas cloud is incredibly slim. But on the surface of a dust grain, it's like a dedicated meeting place, a cosmic trading post where the business of chemistry can finally get done. And that's only the beginning. In these extreme environments, these dust grains don't stay bare for long. They quickly become coated in a shell of frozen ices, not just water ice, but a complex cocktail of frozen gases like carbon monoxide, carbon dioxide, ammonia, and methane. This icy mantle transforms each dust grain into a ready-made chemical reactor. Now, the surface chemistry becomes even more complex. An atom of hydrogen might skate across the icy surface until it meets an oxygen atom, forming a hydroxyl group. Another hydrogen atom arrives, and suddenly you have a molecule of water locked into the ice. This process, known as surface catalysis or grain surface chemistry, is how simple atoms are built into the complex molecular inventory of the cosmos. The incredible cold is the essential enabler here. It keeps these newly formed molecules trapped on the grain, allowing them to accumulate and undergo further reactions, rather than simply flying back off into space. It's a slow, patient process taking millions of years, but it's how these frozen vaults become stocked with organic riches. The products of this slow-motion chemistry are astonishing. Astronomers, by studying the infrared light that these ices absorb, have identified a veritable prebiotic soup frozen onto these grains. We've found the basic ingredients: water, ammonia, methane. But we've also found more complex organic molecules like methanol and ethanol. And there are strong hints of even more exciting compounds, such as formaldehyde and acetaldehyde, which are known to be stepping stones in the formation of amino acids, the very building blocks of proteins and life as we know it. This means that the vast, dark molecular clouds drifting through our galaxy are not just star factories. They are also chemical factories, silently and methodically assembling the raw materials for biology long before any planets have even formed. The cold doesn't just permit this chemistry, it actively preserves it. These icy mantles act as a deep freeze, protecting these fragile molecules from the destructive power of stellar radiation for eons. This has a direct and profound implication for the origin of life on planets like our own. When a new solar system begins to coalesce from one of these cold clouds, these ice-coated dust grains are incorporated into the mix. They become part of comets in the outer system and asteroids in the inner system. Through countless impacts over billions of years, these celestial delivery trucks ferry water and complex organics to the surfaces of young, barren worlds. The water that fills Earth's oceans and the carbon-based molecules that eventually sparked life very likely hitchhiked here on comets and asteroids that formed in the deep freeze of the outer solar system. So, the dusty, icy matrix of a cold molecular cloud is not an end point. It is a starting point. It is the universe's way of preparing the ingredients for life in a safe, cold environment, and then shipping them across space to warm, rocky planets ready for the next great step in cosmic evolution. Beyond their role as chemical workshops, this combination of dust and ice also plays a crucial role in how we perceive these cold regions of space. To our eyes, a dense molecular cloud appears as a black silhouette, a hole in the starry sky. This is because the visible light from background stars is effectively blocked and absorbed by this dense, dusty material. But that same material shines brightly in other parts of the spectrum, particularly the infrared. The dust grains themselves absorb starlight, heat up slightly, and re-radiate that energy as infrared heat. Meanwhile, the icy mantles have their own unique vibrational fingerprints, absorbing specific wavelengths of infrared light that allow astronomers to identify their composition remotely. So, what appears to our eyes as a dark, empty void is actually a vibrant, complex structure glowing with hidden energy and activity. This dusty, icy matrix is the reason we can study these regions at all. It transforms the invisible processes of cold chemistry into a faint but detectable signal, a whisper from the cosmic deep freeze telling us the story of our own chemical origins. Now, let's push our imaginations even further into the quantum weirdness that extreme cold can unlock by considering one of its most spectacular potential manifestations, superfluidity on a truly cosmic scale. Here on Earth, we can create this bizarre state of matter in highly specialized labs. When liquid helium is cooled to just a few degrees above absolute zero, it undergoes a dramatic transformation. It loses all viscosity, meaning it has zero friction. It can creep up the sides of its container and flow out over the top in a seemingly impossible film. It will form persistent, never-ending whirlpools, and it can even defy gravity. This is a stunning demonstration of quantum mechanics playing out in a visible, tangible way. But the truly mind-expanding question is this: if we can create such a strange state of matter in a small beaker in a lab, could the universe itself be creating it on an unimaginably grand scale within the coldest corners of space? Theorists believe the answer is a resounding yes, and one of the most compelling places to look for evidence is inside the most extreme objects we know of, neutron stars. These are the incredibly dense, city-sized cores left behind after a massive star goes supernova. They are essentially giant atomic nuclei, and their interiors are a physics playground of extremes, including crushing densities and, crucially, intense cold in certain layers. Deep within a neutron star's core, the dominant theory suggests that neutrons, freed from the constraints of atomic structure, could become superfluid. Think about that for a moment. Not a few milliliters of liquid helium, but an entire ocean of subatomic particles, potentially miles deep, all acting as a single, frictionless quantum entity. This isn't just a wild guess. It might be the key to solving a long-standing puzzle observed from Earth: pulsar glitches. Pulsars are rapidly spinning neutron stars that act like cosmic lighthouses, sending out beams of radiation with incredibly precise regularity. Their rotational periods are more reliable than most atomic clocks, but occasionally, and without warning, a pulsar will suddenly speed up its spin in a tiny, sudden jump, a glitch. For decades, astronomers struggled to explain where the energy for this sudden change could come from. The leading explanation now involves the idea of interior superfluidity. Imagine the outer crust of the neutron star, a rigid shell of iron nuclei spinning at a constant rate. Meanwhile, inside, a vast superfluid of neutrons is spinning along with it, but because it's a frictionless superfluid, it can spin at a slightly different rate. Theorists propose that this superfluid interior can sometimes become pinned to the solid crust by magnetic flux tubes. As the crust gradually slows down over centuries due to emitting energy, the superfluid core, unaffected by this breaking, continues spinning fast. This creates a rotational differential, a kind of stored energy. When the pinning suddenly breaks, this pent-up energy is transferred catastrophically to the crust, causing it to speed up in the blink of an eye, the glitch we observe. This elegant solution to a 50-year-old mystery shows how a quantum phenomenon born of extreme cold could be governing the behavior of the most massive objects in the universe. But the potential for cosmic superfluidity doesn't stop at the boundaries of neutron stars. Some of the most speculative and exciting theories suggest that even the mysterious dark matter that makes up most of the mass in the universe could exhibit superfluid properties in the cold, dense halos surrounding galaxies. If certain types of dark matter particles are very light and behave as bosons, they too could condense into a frictionless state in the cold depths of galactic halos. This dark matter superfluid could then interact very weakly with normal matter, potentially modifying the laws of gravity on galactic scales and helping to explain other lingering mysteries in astronomy. While this remains a highly theoretical frontier, it powerfully illustrates a profound point. The physics of the ultra-cold, which we once thought was a niche laboratory curiosity, might actually be one of the most important governing principles in the cosmos, operating silently in the background from the smallest scales to the largest. The search for evidence of this is incredibly challenging, often involving subtle deductions from the rotational curves of galaxies or the precise timing of pulsar spins, but it continues to drive observational and theoretical work forward. It reaffirms that these cold environments are not passive backdrops. They are dynamic arenas where matter is pushed to its absolute limits, revealing a universe that is far more interconnected and wonderfully stranger than we ever dreamed. Yet this faint, cold whisper is far more than a simple relic. It is the universe's very first baby picture, a detailed snapshot of a time when everything was unimaginably hot, dense, and uniform. About 380,000 years after the Big Bang, the expanding cosmos had finally cooled enough for protons and electrons to combine into neutral hydrogen atoms. In that pivotal moment, a universe that had been an opaque, searing fog of plasma suddenly became transparent. The light that had been trapped within, scrambling to get free, was finally released in a tremendous flash that has been stretching and cooling ever since, all the way down to its current frigid state. What we detect today as that gentle microwave static is that first flash of light, now redshifted by the unimaginable expansion of space over nearly 14 billion years. It is the oldest light we can possibly see, and it carries within its subtle patterns an encoded message from the dawn of time itself. The true revolutionary discovery about the CMB wasn't just its existence, but its incredible structure. When we map this ancient light with exquisitely sensitive instruments like the Planck satellite, we don't see a featureless, uniform glow. Instead, we see a tapestry of tiny temperature variations, minute fluctuations where some patches are ever so slightly warmer or colder than the average. These fluctuations are incredibly small, on the order of 1 part in 100,000, but they are arguably the most important patterns in the entire cosmos. They represent the primordial seeds of all structure. Those slightly denser, slightly warmer spots were regions where gravity had a tiny bit more material to work with. Over billions of years, gravity relentlessly amplified these tiny differences, pulling more and more matter into those dense spots. The result, those infinitesimal wrinkles in the fabric of the early universe, grew into the vast cosmic web we see today. The great clusters of galaxies, the long filaments of dark matter, and the immense voids that separate them. The entire architecture of our modern universe was imprinted in that first cold light. This reveals a profound truth about cold in the cosmos. It is not a state of passive inactivity, but a crucial and dynamic player in evolution. The CMB's pervasive chill provides the baseline, the ultimate heat sink against which all other cosmic processes are measured. It sets the stage upon which the drama of structure formation unfolds. The coldness of the CMB means that gas in the early universe could effectively cool and condense, falling into the gravitational wells carved out by those primordial density fluctuations. Without this foundational cold to remove thermal energy, the gas might have remained too hot and too diffuse for gravity to ever gather it into galaxies and stars. The universe would have remained a featureless, expanding haze. So, this ancient echo of cold is not just a fossil. It is an active ingredient that continues to influence how gas flows, cools, and collapses across the cosmos even today. Furthermore, the CMB's cold glow is not just something we look at, it's something we must look through. For astronomers studying any other cold object in the universe, a dark molecular cloud, a distant gas giant exoplanet, or a frigid nebula, the faint, uniform bath of the CMB is always there in the background. It is the universal floor for infrared and microwave emissions. To accurately measure the true temperature and properties of these other cold objects, scientists must first subtract this pervasive background signal. It's the ultimate scientific calibration tool, the constant hum of the universe that must be accounted for to hear the specific melody of any individual cosmic source. This makes the CMB an indispensable reference point, the cold baseline that allows us to accurately interpret the strange activity happening in all the other chilly corners of space we explore. Its presence is a reminder that the universe's first state of being was one of intense, energetic heat that has been steadily and inexorably cooling toward this profound and structured silence, a process that gave birth to everything we see, and will ultimately define the cosmos's far future. While we've explored frigid nebulae and interstellar clouds light years away, one of the most significant deep freezes in the entire cosmos might be right here in our own celestial backyard, a vast and distant shell of icy wanderers known as the Oort Cloud. Envision our solar system not as a flat disk of planets ending at Neptune, but as a spherical halo of frozen debris stretching nearly halfway to the next star, a colossal reservoir of trillions of icy objects held in the sun's gravitational grasp at the very frontier of its influence. Out here in this profound isolation, the temperatures are a mere 5 degrees above absolute zero, a near-perfect stasis where time itself seems to stand still. This isn't just a collection of random space rocks, it is the solar system's ultimate attic, a frozen archive preserving the most pristine, unaltered building blocks from the very dawn of our planetary neighborhood some 4.5 billion years ago. The existence of the Oort Cloud remains, for now, a brilliant and necessary hypothesis, a scientific deduction born from the need to explain the behavior of certain comets. Unlike short-period comets that orbit within the realm of the planets, we observe long-period comets that swoop in from every conceivable direction, not just from the flat plane of the solar system. Their orbits suggest a spherical source, a vast cloud of icy bodies surrounding us. The material in this cloud is thought to be the leftover rubble from the formation of the giant planets. In the solar system's violent youth, the gravitational kicks from Jupiter and Saturn likely hurled a significant fraction of their construction debris out to these unimaginably distant reaches, where the sun's warmth is a faint memory and its gravity is just barely strong enough to maintain a hold. The incredible cold of this region is the key to its incredible preservation. Chemical reactions are frozen solid. Radiation from the sun and distant stars has barely made a dent over the eons. These icy bodies are essentially time capsules, storing a perfect chemical record of the primordial soup from which all the planets, including our own Earth, were assembled. But this cosmic deep freeze is not a perfectly secure vault. It is a dynamic and active reservoir, constantly interacting with the larger galaxy. The Oort Cloud does not exist in a vacuum. It is subject to the subtle but persistent gravitational tugs of the galaxy itself. As our solar system orbits the center of the Milky Way, it bobs up and down through the galactic plane and occasionally drifts close to other star systems. Each of these distant gravitational encounters acts like a gentle nudge on the delicate balance holding an Oort Cloud object in place. Every so often, one of these nudges is just right, or just wrong, to dislodge a chunk of primordial ice from its stable orbit and send it on a multi-million-year fall inward toward the sun. This is the moment a dormant relic transforms into a spectacular celestial performer. As this icy nucleus, perhaps just a few kilometers across, begins its long journey into the warmer inner solar system, the sun's radiation starts to work its magic. The deep freeze that has preserved it for so long begins to thaw. Ices that have been solid for billions of years, water, carbon monoxide, methane, ammonia, sublimate directly from solid to gas, erupting from the surface in brilliant jets. These jets act like small thrusters, sometimes causing the comet to spin or even fracture. The released gas and dust form the comet's magnificent atmosphere, or coma, and are then pushed by the solar wind into the iconic tails that can stretch for millions of miles across the sky, one of dust and one of ionized gas, always pointing away from the sun. A seemingly dead and frozen rock, once lost in the deepest dark, becomes a blazing and active world, a temporary and beautiful atmosphere writing its story across the night sky for all to see. This incredible transformation from frozen stillness to vibrant activity is what makes the Oort Cloud so much more than a hypothetical concept. it is a fundamental part of our solar system's ongoing story. These cometary visitors from the deep freeze are more than just a beautiful light show. They are messengers. By analyzing the light from their comas and tails with spectrometers, astronomers can directly sample the composition of the early solar system. Every comet that visits us is delivering a fresh sample of that original planetary building material, and with each visit, we learn more about the conditions that led to our own existence. The water in a comet's ice could hold clues to why Earth has oceans. The complex organic molecules already detected in comets, like the amino acid glycine found on comet Wild 2, tell us that the ingredients for life were being manufactured and stored in the solar system's coldest freezer long before Earth was even formed. The Oort Cloud, in its profound and silent cold, is not a forgotten wasteland. It is a protective ark, a dynamical engine, and a library of our origins, occasionally sending us pages of its frozen records in the form of spectacular comets that light up our heavens and deepen our understanding of where we all came from. But to truly grasp the cosmic significance of these frozen mantles, we must first abandon everything we think we know about ice from our earthly experience. The ice we find in our freezers or on a winter pond is a highly ordered crystalline structure, a rigid lattice of water molecules arranged in a precise, repeating hexagonal pattern. Interstellar ice, forged in the deep cold and vacuum of space, is a completely different beast. It forms not through a slow freeze but through the gradual accretion of individual water molecules, one by one, onto the surface of a microscopic dust grain. This happens so slowly and in such an energy-poor environment that the molecules don't have the chance to organize themselves into a neat crystal. Instead, they land and stick where they fall, resulting in a chaotic, jumbled, and porous solid known as amorphous ice. It's less like a structured lattice and more like a frozen snapshot of a liquid, a disordered, glassy solid that is the most common form of water ice in the universe. This amorphous structure is not an inert scaffold. It's a dynamic and hungry matrix riddled with tiny pores and tunnels, and this is where the true cosmic alchemy begins. As other atoms and simple molecules like carbon monoxide, methane, or even nitrogen bump into this porous, icy mantle in the dark cloud, they don't just bounce off. They get physically trapped within these minuscule cages. These trapped guest molecules, locked in the embrace of the water ice, form what chemists call a clathrate hydrate, a cage-like structure where one type of molecule imprisons another. It's a form of cold storage on a molecular level, and it's incredibly efficient at concentrating the raw ingredients for chemistry in one tiny, focused location. This entire process, from the amorphous structure to the trapping of gases, is only possible because of the profound, near absolute zero cold. Any significant warmth would provide the energy needed for the molecules to rearrange into boring, ordinary crystalline ice and would allow the trapped gases to instantly escape, shutting down the entire chemical factory before it even started. The magic of this system isn't just in its storage capacity, but in its incredible potential for release. These ices are not permanently frozen in time. When a slight perturbation occurs, perhaps the gentle shockwave from a distant supernova, or the warmth of a newly forming protostar beginning to glow nearby, the temperature of a dust grain might rise by just 10 or 20 degrees. This minuscule amount of energy is enough to trigger a profound transformation within the ice mantle. The amorphous ice, which is metastable, suddenly undergoes a rapid phase change, spontaneously reorganizing itself into a more stable crystalline structure. This process of crystallization is exothermic. It releases a small but significant burst of energy. More importantly, as the ice structure tightens and changes, it squeezes out all of those trapped guest molecules that were once imprisoned in its pores. This sudden, localized release is like popping open a trillion tiny champagne corks all at once, flooding the immediate vicinity around the dust grain with a concentrated cloud of reactive molecules. Now the real chemistry can begin in earnest. This sudden injection of energy and the dense crowd of newly released molecules create a frenzy of activity. Simple carbon monoxide molecules, now free and buzzing with this slight thermal energy, can link together into long carbon chains. Hydrogen atoms skating across the now crystalline ice surface can readily bond with carbon atoms to form complex hydrocarbons. Radicals, highly reactive molecular fragments, can find each other and combine into ever larger and more complex organic structures. This process, known as a CO explosion, or more generally as non-thermal surface chemistry, is thought to be one of the primary engines for creating the complex molecules that are the precursors to life. And it's all driven by the bizarre properties of the ice itself changing phase, a transformation that is itself triggered by the slightest hint of warmth in an otherwise eternally cold environment. We have observational evidence that this isn't just theoretical. In vast stellar nurseries like the Taurus Molecular Cloud, astronomers using telescopes like the Atacama Large Millimeter Array (ALMA) have been able to peer into these regions and detect the spectral fingerprints of these complex ices and the molecules they produce. They've found not just water and carbon monoxide, but methanol, ethanol, formaldehyde, and even more complex molecules like methyl formate and dimethyl ether. Some of the most exciting detections are of molecules like glycolaldehyde, a simple sugar, and ethanolamine, a component of cell membranes. Each of these discoveries paints a picture of a factory line operating in the cold dark, where simple ices, through their unique structures and phase changes, are methodically assembling the very pieces that could one day become the foundation of biology on a new world. The ice isn't a passive stage for this drama. It is an active participant, a catalyst, and an energy source, all rolled into one. Its strange, non-earthly properties are the essential drivers that turn the silent, cold void into a vibrant chemical reactor, proving once again that in the cosmos, stillness is often just the quiet before a storm of creation. While we often picture the spaces between stars as vast and empty, they are in fact teeming with immense structures of cold gas, floating like ethereal islands in the galactic sea. These are not the dense molecular clouds where stars are born, but their more diffuse and widespread cousins, atomic and molecular hydrogen clouds with temperatures ranging from a bone-chilling 10 to 100 degrees above absolute zero. They are the fundamental raw material of a galaxy, the unseen reservoir from which future generations of stars will eventually draw their substance. This cold gas doesn't just passively exist, it forms the very circulatory system of a galaxy, a dynamic medium that governs its growth, evolution, and overall metabolism over billions of years. The very existence of these colossal, chilly structures presents a fascinating puzzle to astronomers. On the surface, the physics seems straightforward. Gravity should simply cause these vast collections of gas to relentlessly collapse inward upon themselves, rapidly condensing into stars until the reservoir is completely depleted. But when we look out at galaxies like our own Milky Way, we see that this isn't happening. These clouds persist for astonishingly long periods, often for tens of millions of years, all the while resisting gravity's constant pull. The secret to their longevity lies in a delicate and powerful balancing act, a cosmic tug of war between the force of collapse and two powerful opposing agents, turbulence and magnetic fields. Within these clouds, supersonic turbulence acts like a powerful internal storm, with shock waves and chaotic motions ripping through the gas, constantly stirring it up and providing enough outward pressure to support the cloud against its own weight. At the same time, pervasive magnetic fields, woven through the cloud like an invisible spiderweb, provide a supporting skeleton. Ionized particles within the gas become trapped along these field lines, and their resistance to moving across the magnetic direction creates a form of support that can effectively put a pause on gravitational collapse. It's this intricate interplay, this organized chaos, that allows these clouds to live long, productive lives, acting as stable nurseries where star formation can be a slow, regulated process rather than a sudden, catastrophic burst. Modern astronomical technology has allowed us to peer into the heart of this chaos and discover an unexpected level of order. When we use radio telescopes to map the distribution of this cold gas, we don't see formless, amorphous blobs. Instead, we find that the universe has a pronounced preference for weaving gas into incredibly long, thin, and coherent structures. These are the interstellar filaments, immense ribbons of cold gas and dust that can stretch for dozens, sometimes even hundreds of light years across the galaxy, while often being less than a single light year thick. It's as if the galaxy is a loom, and the forces of turbulence, magnetism, and gravity are the threads weaving a tapestry on an unimaginable scale. The formation of these filaments is a core prediction of what's known as the turbulent cascade model, where energy from large-scale motions in the cloud trickles down to smaller and smaller scales, naturally organizing matter into these elongated, thread-like structures. They are not simply curiosities, they are the fundamental arteries of star formation. Observations from telescopes like Herschel have shown conclusively that stars prefer to be born in the densest knots within these filaments, where the gas has been compressed to the point that gravity can finally win its long battle against its opponents. Yet for all our progress, the precise mechanics behind the stability and evolution of these filaments remains an active and thrilling frontier of research. How exactly do magnetic fields interact with the turbulent gas to sculpt and support these shapes over such long timescales? What determines a filament's ultimate fate, whether it will simply dissipate back into the diffuse medium, or whether it will fragment into a string of new stellar systems? Each new observation seems to reveal another layer of complexity, showing that these cold regions are not simple, placid environments, but are instead vibrant arenas where the fundamental forces of the universe engage in a continuous and intricate dance. This dynamic equilibrium, this beautiful tension between creation and dissolution, is precisely what makes these chilly galactic clouds such incredible hotbeds of activity. They are the engines of galactic ecology, the cradles of new suns, and the proof that even in the deepest cold, the universe is constantly at work, weaving structure out of chaos. And just when we think we've grasped the full extent of cold's creative potential, we journey to the frozen moons of the outer solar system, where we find one of the most stunning paradoxes in all of cosmology. Worlds with surfaces harder than steel and colder than a winter night on Pluto, yet somehow firing massive, brilliant plumes of water vapor and ice crystals hundreds of kilometers. Space, this is cryovolcanism, and it completely shatters our traditional understanding of what it means for a planetary body to be active. On Earth, volcanoes are driven by internal heat and molten rock. But on moons like Saturn's Enceladus or Jupiter's Europa, the volcanoes erupt water, ammonia, methane, and other volatiles, an icy slurry that freezes instantly in the vacuum of space, creating vast, shimmering curtains of ice particles. The surface temperatures on these worlds are almost incomprehensibly cold, routinely plunging to -200 degrees Celsius or lower, a deep freeze that should lock every molecule into a state of perpetual, rigid stasis. The fact that they are anything but dormant is a clue that something extraordinary is happening beneath the ice. The engine for this incredible activity is not the radioactive decay that powers Earth's geology, but a far more subtle and continuous force, tidal friction. These moons do not travel on simple, circular orbits around their parent planets. They are yanked and squeezed by the immense gravity of their gas giant hosts, as well as by the gravitational pulls of their sibling moons. This constant, rhythmic flexing generates immense internal heat. It's the same principle as repeatedly bending a metal coat hanger eventually. The point where it flexes becomes very warm to the touch. On a planetary scale, this process can generate enough energy to melt vast reservoirs of ice into liquid water oceans, maintaining them in a liquid state for billions of years despite the cryogenic shell that encases them. This creates the fundamental condition for cryovolcanism, a warm, liquid interior desperately trying to find a way out through a cold, brittle, frozen outer crust. The evidence for this is no longer theoretical. It's been witnessed in breathtaking detail. The Cassini spacecraft didn't just detect the plumes of Enceladus. It flew directly through them, its instruments tasting and analyzing their composition. The findings were nothing short of revolutionary. The plumes were not just simple water vapor. They were a complex cocktail containing salty water ice, silica nanoparticles, and a suite of organic molecules including methane, propane, acetylene, and formaldehyde. Most stunning of all was the detection of molecular hydrogen, a gas that on Earth is often a telltale sign of methanogenesis, a metabolic process used by microbes living in hydrothermal vents deep under our oceans. The data pointed irresistibly to a specific scenario, a deep, global saline ocean lying beneath Enceladus's ice shell, interacting with a hot, rocky seafloor through hydrothermal vents. On Europa, the evidence is equally compelling. The Hubble Space Telescope has observed what appear to be transient water plumes erupting from its surface, while detailed images of its icy crust show a fractured, jumbled, and young surface, geologically speaking, indicating that it is frequently being resurfaced by material from the ocean below welling up through the cracks. This transforms these icy moons from frozen, dead rocks into the most promising abodes for life beyond Earth we have yet discovered. The formula, as we understand it, requires three key ingredients: liquid water, a source of energy, and the right chemical building blocks. The tidal heating provides the energy. The global subsurface oceans provide the liquid water in volumes that may dwarf all of Earth's oceans combined. And the complex organic molecules found in the plumes, coupled with the mineral-rich soup that would be created by water interacting with a rocky core at hydrothermal vents, provide the chemistry. The extreme cold of the surface crust is not a barrier to this process, it is a protective lid. It shields the delicate, warm, liquid interior from the harsh radiation and vacuum of space, creating a stable, isolated environment where life could potentially originate and thrive, completely independent of the sun's energy, much like the ecosystems we find thriving in the eternal darkness at the bottom of our own oceans. Cryovolcanism is therefore the universe's grand reveal, the dramatic signal that betrays the hidden, vibrant world below. Each plume is a free sample, a direct ejection from a potentially habitable environment, delivering material that future missions could easily collect and analyze without even having to land. These eruptions exemplify the core theme we've seen again and again, that the coldest exteriors in the cosmos are most often masks, concealing and protecting incredible internal dynamism. They teach us that a world should never be judged by its frozen, cratered surface alone, for beneath the most barren and icy facade, there might just be a warm, dark, organic, rich ocean waiting to be explored, holding answers to the oldest question of all: are we alone in the universe? Now, as we push deeper into the cosmic cold, we encounter perhaps the ultimate enigma, a mystery that doesn't just reside in these chilly realms but may be fundamentally shaped by them, the puzzle of dark matter. This invisible substance, which makes up roughly 85% of all matter in the universe, is famously aloof. It doesn't emit, absorb, or reflect light, and it seems to breeze through normal matter as if it weren't even there. It doesn't have a temperature in the way we normally think of it, because it doesn't interact with the electromagnetic forces that would allow it to thermalize. But its influence, its sheer gravitational weight, is absolutely paramount in shaping the largest structures in the cosmos, and this influence becomes especially pronounced in the coldest, densest environments we can find. To see this gravitational hand at work, we need to look at the majestic assemblies of galaxies known as clusters. These are the universe's true metropolises, containing thousands of galaxies all bound together by gravity. But the stunning reality is that the visible galaxies themselves are just the lit-up skyscrapers in a much larger city. They account for only a tiny fraction of the cluster's total mass. The majority is made up of two invisible components: a superheated plasma that fills the space between the galaxies, and an immense, overarching halo of dark matter that provides the gravitational glue holding the entire structure together. It's within these massive halos of dark matter that the coldest, densest gas in the universe is often found. The incredible gravitational pull from the dark matter compresses this intracluster gas, increasing its density to extraordinary levels. When gas is compressed this way, it becomes incredibly efficient at radiating away its thermal energy, cooling itself down dramatically. This enhanced cooling has a direct and puzzling consequence. It can trigger massive, runaway waves of star formation within the cluster's central galaxy, creating stellar bursts of such intensity that they defy our standard models of galactic evolution. The dark matter's gravity, by creating the conditions for profound cold, is indirectly dictating the pace of creation itself. This relationship becomes even more intriguing when we zoom in from giant clusters to the smaller, colder scales of dark molecular clouds. The prevailing theory of structure formation, known as the lambda cold dark matter model, suggests that all galaxies, and by extension the stars within them, are built within these vast, nested halos of dark matter. A giant molecular cloud, the birthplace of millions of stars, isn't just floating freely in space. It's likely ensconced within its own smaller, local halo of dark matter. The gravitational field from this halo could be applying a subtle, constant pressure on the cloud, further encouraging the gas to condense and cool. Some astrophysicists speculate that this additional compression from dark matter might be a crucial, yet overlooked, factor in solving the long-standing mystery of how some clouds collapse to form stars far more efficiently than our theories predict. The presence of unseen matter could be creating the perfect cold, high-pressure environment for star formation to flourish, making dark matter not just a cosmic architect on the largest scales, but a silent partner in the birth of individual stars. But what if dark matter's role in the cold cosmos is even stranger and more direct? This is where we venture into the realm of highly speculative but utterly fascinating theoretical physics. We've already seen how matter at ultra-cold temperatures can exhibit bizarre quantum behaviors, like forming Bose-Einstein condensates where countless particles act as one. What if certain types of dark matter particles could do the same thing? If a hypothetical dark matter particle is extremely light and what physicists call a boson, then in the cold, dense confines of a galactic halo, these particles could potentially lose their individual identities and merge into a giant, galaxy-sized Bose-Einstein condensate. This wouldn't be a condensate made of atoms, but of the very fabric of dark matter itself. In this exotic state, the rules of behavior could change dramatically. This collective, quantum fluid-like behavior could potentially explain some of the lingering puzzles we observe in the way galaxies rotate, offering a new perspective on how dark matter distributes itself and interacts gravitationally on smaller scales. The profound cold of space, therefore, might provide the ideal laboratory for dark matter to finally reveal some of its secrets. In the frenetic, high-energy environments of the early universe or near black holes, any subtle, low-energy interactions that dark matter might have would be completely washed out. But in the deep, quiet freeze of a galactic halo or a molecular cloud, where thermal noise is virtually non-existent, those same subtle signals might be amplified. It's the ultimate example of needing to slow things down to see them clearly. While these ideas remain at the cutting edge of cosmology, they powerfully illustrate a profound and humbling truth. The answers to the universe's biggest mysteries may not be hidden in the blazing infernos of stars, but in the silent, gravitational embrace of the cosmos's coldest and darkest corners, waiting for us to learn how to listen to their faint, frozen whispers. This bizarre but fundamental rule of the quantum world is called quantum tunneling, and it acts as a master key, unlocking chemical possibilities in the cosmic deep freeze that would otherwise be permanently sealed shut. To understand how it works, picture a very simple, everyday scenario. Imagine you're rolling a ball up a hill. If you don't give it enough of a push, it will roll back down to you. It simply doesn't have the energy to get over the top. In the realm of chemistry, this hill is an energy barrier. The minimum amount of kinetic energy two atoms need to collide with in order to get close enough for their electron clouds to interact and form a chemical bond. In a warm environment, atoms are zipping around with plenty of thermal energy, easily vaulting over these barriers to create new molecules. But in the profound cold of an interstellar cloud, where atoms are moving with agonizing slowness, that necessary energy is completely absent. By all the classical rules of chemistry that we learned in school, these reactions should be utterly impossible. The atoms should just meekly bounce off each other and go their separate ways forever. But the quantum universe operates on a completely different set of rules, one where particles are not just tiny balls, but also behave as smeared-out waves of probability. This wave-like nature means an atom isn't confined to a single, precise location. Instead, it exists within a fuzzy cloud of potential locations, and there's a very small but non-zero probability that it could actually find itself on the other side of that energy barrier without ever having to go over it. It's not that the atom magically jumps or teleports. It's more that the energy barrier becomes semi-transparent to the atom's wave function. There's a tiny chance it can simply appear where it's technically forbidden to be, effectively tunneling through the mountain instead of climbing it. The colder the environment, the more significant this tunneling effect becomes, because without thermal energy to provide the classical push, tunneling becomes the only game in town. It's the universe's ultimate cheat code, allowing chemistry to proceed in places that are, by traditional standards, far too cold for anything to ever happen. The most important and foundational reaction in the entire universe is the formation of molecular hydrogen, two hydrogen atoms coming together to form an H2 molecule. This is the first step in building everything else, the primary fuel for stars and the raw material for making water and organic molecules. But there's a huge problem. When two lone hydrogen atoms meet, they repel each other slightly before they can get close enough to bond. Overcoming that repulsion requires a significant energy barrier. In the near absolute zero temperatures of a dark cloud, these atoms simply do not possess the thermal energy to overcome it. For decades, astronomers were baffled about how so much molecular hydrogen could exist in space. The answer, we now know, is quantum tunneling. The wave nature of the ultra-cold hydrogen atoms allows them to tunnel through that repulsive barrier with just enough frequency that, over the immense volume and timescales of a molecular cloud, H2 molecules form in astounding abundance. Without this quantum effect, the universe would be filled with nothing but lonely hydrogen atoms, and the rich chemistry needed for stars and planets and life could never begin. This process doesn't stop with simple hydrogen. Quantum tunneling is the secret engine behind the assembly of far more complex molecules in these icy nurseries. Consider the formation of water ice on a dust grain. A common pathway involves an oxygen atom bonded to a hydrogen atom, forming a hydroxyl radical, O meeting a second hydrogen atom. For them to form a water molecule, they must overcome an energy barrier. In the cold, tunneling makes this possible. This same principle applies to the construction of organic molecules. A hydrogen atom tunneling through a barrier can add itself to a carbon monoxide molecule frozen on an ice grain, beginning a chain of reactions that can lead to formaldehyde, methanol, and even more complex prebiotic compounds. The incredible slowness of each individual tunneling event is completely offset by the sheer number of attempts happening simultaneously across trillions of dust grains over millions of years. What seems like an impossibly rare occurrence becomes an inevitable and efficient factory process on a cosmic scale. This revelation fundamentally changes our perception of these cold regions. They are not frozen wastelands where chemistry is shut down. They are instead quantum-controlled laboratories where the rules are rewritten. The deep cold suppresses the noisy, chaotic thermal reactions, creating a quiet, orderly environment where these subtle quantum effects can dominate and direct the chemical evolution of matter. It's a perfect marriage of physics and chemistry, showing that the two disciplines are not separate but deeply intertwined in the fabric of the cosmos. The strange activity we detect in these clouds, the vast arrays of complex molecules, is a direct signature of quantum mechanics operating in plain sight, on a galactic scale, proving that the universe is not just stranger than we imagine, but that it operates on a level of ingenuity that continues to humble and inspire our quest for understanding. Leaving behind the familiar icy moons of our own solar system, we now cast our gaze across the light years to worlds orbiting distant suns, where the concept of cold is redefined on an almost unimaginable scale. Among the thousands of exoplanets discovered, some stand out not for their warmth, but for their profound, almost absolute chill. These are the frozen super-Earths and ice giants adrift in the outer reaches of their star systems or wandering alone in the dark between stars. A prime example is the poetically named Ogle 2005 BLG 390Lb, a world detected through the gravitational microlensing technique, a method perfectly suited for finding these distant, dark orbs. This particular planet, roughly 5 times the mass of Earth, orbits a faint red dwarf star at a distance so vast that its year is equivalent to about 10 Earth years. Out there, the feeble starlight provides virtually no warmth, allowing the surface temperature to plummet to around -220 degrees Celsius. At such extremes, the very nature of matter and atmosphere transforms into something utterly alien. The most immediate and dramatic transformation occurs in the planet's atmosphere, provided it has managed to hold on to one. On a warm world like Earth, our atmosphere is a permanent gaseous envelope, but on a planet like this, the atmosphere can literally freeze solid and collapse. Gases we think of as permanent, like nitrogen, oxygen, or methane, can condense directly out of the sky, falling as snow and accumulating in vast glacial deposits on the surface. Imagine a landscape where the ground beneath your feet isn't rock or water ice, but frozen air, great plains of solid nitrogen, mountain ranges of solidified oxygen, and dunes of carbon dioxide snow. The entire sky could be clear and perpetually black, devoid of any scattering gases, offering a crystal clear view of the starscape above, because all the atmosphere has literally frozen onto the surface. In some models, these worlds might only temporarily possess an atmosphere during brief, volatile-driven warming events, perhaps from tidal heating or internal geological activity, only for it to once again snow out and vanish as the planet returns to its deep freeze state. Yet, to assume that such profound cold equates to a dead, static world would be a grave mistake. These planets may harbor their own sources of internal dynamism, creating weather and geology that is bizarre beyond comprehension. Even in the deepest cold, radioactive elements in the planet's core continue their slow decay, providing a trickle of internal heat. This heat might be enough to power cryovolcanism, but not with water as on Enceladus. On these colder worlds, the cryomagma could be a slush of liquid nitrogen, methane, or even carbon monoxide. Picture a volcano, not spewing fiery rock, but erupting a geyser of supercold liquid nitrogen that instantly flash freezes in the vacuum, creating brilliant, transient plumes of nitrogen ice crystals against the blackness of space. The surfaces themselves could be geologically active, with solid nitrogen glaciers flowing with an impossible slowness, a single centimeter per year, creeping across the landscape over millennia, carving out valleys in a bedrock of water ice. The sheer cold itself becomes a geological agent, making materials that are soft and malleable on Earth as hard as granite, and allowing for tectonic processes we are only beginning to model. Studying these frigid outliers is not merely about cataloging cosmic oddities. It is absolutely crucial for completing our understanding of planetary science. Our solar system provided us with a certain template: rocky worlds inward, gas and ice giants outward. But the exoplanet census has revealed that galaxy is far more creative and disorderly. Planets can migrate vast distances, getting flung into lonely, cold orbits or being captured by stars different from their birth parents. By analyzing the composition and conditions of these cold exoplanets, we learn about the incredible diversity of planetary formation and evolution. They represent one extreme end of the planetary temperature spectrum, teaching us about the limits of atmosphere retention, the phase changes of matter under different pressures, and the potential for geological activity without stellar energy. Each one is a natural laboratory for testing our theories about how all planets, including our own, work. This expansion of our planetary definition directly impacts the greatest question of all, the search for life. The traditional habitable zone is defined as the region around a star where liquid water can exist on a planet's surface. But the discovery of subsurface oceans on icy moons violently shattered that simplistic notion. Similarly, a frozen exoplanet with a surface of solid nitrogen might seem the least likely place for biology. But if tidal forces or radiogenic heat maintain a liquid water ocean beneath a shell of ice dozens of kilometers thick, then that world instantly becomes a prime candidate in the search for life, regardless of its frigid surface temperature. These cold worlds force us to think more broadly about habitability, to consider biosignatures not in atmospheres that may have collapsed, but in the chemical imbalances that might be detected in plumes from cryovolcanos or in the subtle heat signatures bleeding through the ice from a hidden ocean below. They are a powerful reminder that activity and potential are not the sole domain of the warm, and that the universe's most fascinating secrets are often hidden in plain sight, shrouded in the most beautiful and extreme deep freeze. While the profound cold of these regions quiets the thermal chaos, it simultaneously amplifies the influence of another, more subtle cosmic force, magnetism. In the frigid, dense hearts of molecular clouds, magnetic fields become the invisible architects of structure, weaving through the gas and dust like ethereal threads that can both support and sculpt the birth of new stars. These fields are not mere spectators. They are generated and amplified by the slow, churning motions within the cloud itself, and once established, they fundamentally change the rules of the game. Imagine trying to stir a bowl of iron filings mixed with oil. The filings would align with the motion, creating patterns. On a cosmic scale, the ionized particles within a cloud act like those filings, tracing out the magnetic field lines and revealing a hidden skeleton that governs everything from the grandest flows to the tiniest dust grain. This magnetic scaffolding performs a critical balancing act against the relentless pull of gravity. Without it, a dense cloud would collapse into stars in a frantic, short-lived burst. But the magnetic field provides a powerful supporting pressure, effectively propping the cloud up and significantly slowing its descent into collapse. It's a cosmic tug of war where the field lines, frozen into the ionized component of the gas, create a resistant force that gravity must work against. This magnetic support is so effective that it can put star formation on pause for millions of years, allowing the cloud to evolve and structure itself gradually. For a collapse to finally begin, this magnetic brake must be released, a process thought to occur through a slow leakage of neutral particles drifting past the ions locked to the field lines, a delicate diffusion that gradually undermines the field's support and allows gravity to finally win. Yet, in a beautiful paradox, these same magnetic fields that prevent collapse are also responsible for creating the very structures where stars are born. As turbulence and motion twist and compress the field lines, they channel material into incredibly long, thin filaments. These are not random formations. They are the direct result of magnetic forces guiding and focusing flows of matter. Observations from telescopes like Herschel have shown us that the cosmos has a pronounced preference for weaving its cold gas into these intricate, thread-like structures that can stretch for dozens of light years. The magnetic fields running along these filaments act like cosmic rails, guiding material inward toward the densest knots, which become the seeds of future stars. In this way, magnetism doesn't just hinder star formation, it organizes it, creating the efficient pipelines that feed growing protostars. The extreme cold is the essential enabler for this magnetic dominance. In a warmer environment, intense thermal motion would keep particles highly ionized and chaotic, making it difficult for magnetic fields to maintain coherent control over such a turbulent plasma. But in the deep freeze of a molecular cloud, the level of ionization drops dramatically. Only a tiny fraction of particles are ionized enough to become locked to the magnetic field lines. This actually increases the field's influence per particle, allowing it to dictate the motion of the entire cloud by guiding this minority of charged particles, which then collide with and drag the vast majority of neutral atoms and molecules along with them. The cold creates a quieter, more orderly environment where these subtle magnetic forces can orchestrate the motion of an entire gas cloud light years across. We can actually see the handiwork of these magnetic fields in the subtle details of the light that reaches us. Non-spherical dust grains, shaped like tiny needles or rods, do not tumble randomly in the void. The magnetic fields cause them to spin and align their long axes perpendicular to the direction of the field lines. When starlight passes through a cloud filled with these aligned grains, it becomes polarized, its light waves oscillating in a preferred direction. By measuring this polarized light, astronomers can literally map the magnetic field structures within these dark clouds, turning starlight into a probe for invisible forces. Furthermore, the dust itself emits light at submillimeter wavelengths, and this emission is also polarized, providing another independent way to chart the magnetic landscape within these stellar nurseries. This isn't just theoretical, it's observed data that confirms the magnetic fields are intimately tangled with the birth of every star. So, when we peer into a dark molecular cloud, we are not looking at a simple battle between cold and gravity. We are witnessing a complex magnetic choreography where three powerful forces, gravity, turbulence, and magnetism, engage in a dynamic dance. The profound cold tilts the balance, allowing magnetism to emerge as a primary director of this cosmic ballet. It shapes the clouds into filaments, supports them against their own weight, guides their collapse, and even aligns the very dust from which planets will one day form. This reveals that the strange activity in these cold regions is not a product of temperature alone, but a symphony of physics where the invisible force of magnetism plays a leading role, conducting the flow of matter that will one day ignite into new suns. Yet, even as we chart the influence of magnetic fields sculpting cold gas, we encounter a state of matter that seems to defy its own fundamental nature, a substance that by all rights should be searingly hot, forced into a paradoxical existence within the cosmic chill. We are talking about plasma, the fourth state of matter, an ionized soup of electrons and atomic nuclei that typically requires immense temperatures to tear atoms apart. We find it in the hearts of stars and in lightning bolts, but in the cold, sparse outskirts of nebulae or the tenuous fringes of planetary magnetospheres, this same plasma undergoes a bizarre transformation. It becomes supercooled, a substance trapped in a state of charged excitement despite being immersed in a deep freeze that should have long ago forced it to calm down and recombine into neutral atoms. This isn't a plasma sustained by internal heat. It's a plasma kept alive by its own profound isolation or by a steady, gentle drizzle of external energy. The secret to this strange existence lies in two key factors: incredibly low density and external radiation. In the near-perfect vacuum of deep space, the density of particles is so fantastically low that an electron freed from its atom might travel for miles before it ever encounters a positive ion to recombine with. This drastically prolongs its ionized state, creating a plasma that can persist for astonishingly long periods, even at temperatures just a few degrees above absolute zero. Furthermore, this tenuous gas can be kept perpetually ionized by a faint but constant bath of radiation from distant stars, cosmic rays, or even the ubiquitous glow of the cosmic microwave background. This external energy source is just enough to continually knock electrons loose, maintaining the plasma's charged state without ever providing the significant thermal energy we normally associate with such a lively condition. It's a delicate balancing act between a trickle of energy in and an incredibly slow rate of energy loss, creating a stable yet bizarre form of matter. This supercooled condition leads to behaviors that are almost the opposite of what we see in their hot, dense counterparts. In a laboratory fusion reactor or the sun's interior, hot plasma is dominated by short-range, violent collisions between particles. But in a supercooled plasma, collisions are so rare that collective, wave-like interactions between particles become the dominant force. Waves of energy can propagate through this cold plasma with unusual clarity and persistence, their interactions enhanced because they aren't being constantly dampened by particle crashes. The plasma can also exhibit a dramatically extended recombination time, where a hot, dense plasma might snap back to a neutral gas in microseconds if its energy source is cut, A supercooled plasma could maintain its ionization for days, weeks, or even longer, simply because its constituent particles are so unlikely to ever find each other again in the vast emptiness. We have compelling evidence that this strange matter isn't just a theoretical curiosity. It's a real and active component of our cosmic neighborhood. Within the protective magnetic bubble of Earth's own magnetosphere, there are vast, cold regions where plasma behaves in these exact ways. The plasmasphere, a donut-shaped region of cold plasma encircling our planet, is a textbook example. Its particles are ionized, yet their temperature is remarkably low. This cold plasma interacts with the hotter, more energetic plasma from the solar wind in complex ways, influencing how energy is stored and released in the magnetosphere, which in turn affects the intensity and behavior of the auroras we see at the poles. Even farther out, in the interstellar medium that drifts between the stars, astronomers believe a significant fraction of the thinly spread gas exists in this supercooled plasma state, a pervasive, charged fog that fills the galaxy. The very existence of this cold plasma forces us to challenge our most basic assumptions about the states of matter. It proves that ionization is not a privilege reserved only for the intensely hot. It can be a permanent, or at least a very long-lasting, condition even in the most frigid environments, dictated not by temperature but by density and external energy input. This revelation adds yet another layer of complexity to the already intricate physics of cold cosmic regions. It shows us that these areas are not simply about the absence of energy, but about a different kind of energy economy, one where subtle, slow, and persistent processes dominate over violent, rapid ones. The supercooled plasma is a perfect example of the universe's ingenuity, taking a phenomenon we think we understand and presenting it in a startling new form when placed in the deep freeze, reminding us that in the cosmos, the rules are always more flexible and more wonderful than we first imagined. Now, let's turn our attention to one of the most dynamic and visually stunning structures in the cosmos, the accretion disk. We often picture these vast, swirling platters of gas and dust as uniformly brilliant and searingly hot, glowing with the fierce energy of friction and gravity as they spiral inward toward a central star or black hole. But this picture is incomplete. Within these cosmic whirlpools, there exists a profound and consequential temperature gradient, a dramatic shift from the fiery inner rim to a far more frigid outer domain. It is in these distant, cold regions of the disk that some of the most critical and mysterious processes of cosmic construction quietly unfold, governed not by intense heat, but by the patient, ordering power of extreme cold. As material orbits farther from the central gravitational engine, it finds itself in an environment where the fierce radiative heating diminishes dramatically. Here, the particles of gas and dust can effectively radiate away their thermal energy into the void of space, cooling with an efficiency that allows temperatures to plummet to just tens of degrees above absolute zero. This rapid cooling triggers a phase change that is fundamental to building planets, the direct condensation of gaseous molecules into solid, icy grains. Water vapor freezes into tiny crystals of water ice. More volatile compounds like carbon monoxide and methane also freeze out, coating dust particles in intricate layers of exotic frost. This isn't a simple cosmetic change. It is the very moment that the raw material for future worlds transitions from a diffuse, gaseous state into tangible, solid seeds. The growth of these icy mantles dramatically increases the solid mass available in the disk, providing vastly more material for the next crucial step, the gathering of these microscopic particles into ever larger bodies through collisions and sticky coagulation, a process that begins the long journey from tiny grain to massive planet. The presence of this cold, solid material doesn't just add mass, it fundamentally rewrites the physical rules governing the entire disk's behavior. One of the most critical properties of an accretion disk is its viscosity, its effective internal friction, which dictates how quickly material can spiral inward to feed the central object. In the classic model of a hot, ionized disk, magnetic fields are thought to provide this viscosity through a process called magnetorotational instability. But in the cold, neutral outskirts of the disk, this mechanism shuts down. The gas is too cold to remain significantly ionized, and without charged particles, magnetic fields cannot effectively couple to the material. This creates a fascinating dilemma. The cold outer disk can be incredibly rich in solid material, yet it may be largely cut off from efficiently feeding that material inward due to its low viscosity. This very impediment might be a blessing in disguise for planet formation, as it allows the solid building blocks to accumulate and grow over long periods without being rapidly devoured by the central star. Perhaps the most spectacular consequence of this cold material is its role in launching the immense, focused jets that often erupt from the poles of young stellar objects. The prevailing theory for how these hypersonic jets are formed and collimated involves powerful magnetic fields that are anchored in the inner, rotating disk. For these fields to effectively grip the disk material and fling it outward, the disk needs to have a certain level of electrical conductivity, which in turn requires a population of free electrons. In the hot inner disk, thermal ionization provides this, but in the cold outer regions, the source of ionization is different. It is likely provided by cosmic rays or the radioactive decay of elements within the dust grains themselves. This subtle, non-thermal ionization in the cold disk may be crucial for allowing the magnetic fields to couple to a much larger reservoir of material, enabling the magnificent, structured outflows that can stretch for light years and regulate the angular momentum of the entire budding solar system. When we shift our gaze from young stars to the most terrifying gravitational engines in the universe, the role of cold accretion becomes even more enigmatic and revolutionary. Supermassive black holes at the centers of galaxies are typically thought to be fed by hot, ionized gas that shines brilliantly as an active galactic nucleus. However, new observations suggest a different, quieter mode of feasting, cold accretion. In this scenario, giant, cold clouds of molecular gas, or even a steady drizzle of cold, condensed gas from a galactic halo, can fall directly toward the black hole. This cold stream is so dense that it doesn't shock heat to millions of degrees as it descends. Instead, it largely maintains its frigid integrity all the way to the precipice of the event horizon. This changes everything about how the black hole consumes its meal and the feedback it provides to its host galaxy. A diet of cold gas is far more efficient and can lead to a much higher accretion rate, yet it may not produce the same brilliant, continuous blaze of radiation as a hot flow. Instead, it might result in more episodic and structured outbursts. We might see periodic, quiet accumulation of cold gas followed by sudden, violent releases of energy as clumps of material finally cross the threshold and are devoured. This cold mode accretion could be the hidden mechanism behind some of the more mysterious and variable activities we see in galactic nuclei, offering a fresh perspective on how these cosmic behemoths grow and how they ultimately dictate the fate of the galaxies they inhabit. The dynamics within these cold disks, whether around a newborn star or a billion solar mass black hole, reveal a universe where the delicate balance between heating and cooling is not a side note, but the central director of cosmic evolution, turning these frigid zones into hotspots for the most consequential and mysterious processes. But just as these cold clouds rely on their internal dynamics, they are also constantly being probed and energized by visitors from far beyond their borders, cosmic rays. These aren't rays of light, but rather a relentless rain of atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light by the most violent events in the galaxy: supernova explosions, merging neutron stars, and the ferocious jets of active black holes. This hail of high-energy particles screams across interstellar space, and when it slams into the frigid, dense environment of a molecular cloud, it acts like a microscopic wrecking ball and a matchstick, simultaneously destroying and creating in a chaotic dance that is utterly essential to the cloud's chemistry. The most immediate effect of a cosmic ray piercing the cloud is ionization. As a high-speed proton tears through the cold, neutral gas, it doesn't often collide head-on with atoms. Instead, its powerful electric field rips electrons away from any molecules it passes near, leaving a trail of ionized and highly reactive particles in its wake. This might seem destructive, and it is. Complex molecules can be shattered by the impact, but in the strange logic of chemistry, this destruction is the first step toward a more complex creation. These newly formed ions are desperate to regain stability, and they will react with almost anything they bump into in the dense cloud, initiating chains of chemical reactions that would be impossible under the cloud's normal, frozen conditions. It's a process that jump-starts chemistry in a place that is simply too cold for thermal reactions to occur at any meaningful rate. The cosmic rays provide the activation energy, acting as a universal catalyst that brews complexity out of simplicity. This is how some of the most intricate molecules in space, including ions that are precursors to amino acids, are believed to form, all thanks to the violent intrusion of these galactic projectiles. This energetic input does more than just drive chemistry. It also plays a crucial role in the cloud's very structure and lifespan. The heat generated by cosmic ray ionization, while minuscule by everyday standards, is significant in an environment where the baseline temperature is only 10 to 20 degrees above absolute zero. This tiny, pervasive heating source acts as a gentle but persistent pressure, counteracting the cloud's tendency to cool itself into a catastrophic gravitational collapse. It helps maintain a level of internal turbulence, keeping the gas and dust stirred up and preventing it from becoming too quiet and stable. This sustained, low-level activity is vital. Without it, a cloud might collapse into stars in a single, brief, and inefficient burst. The cosmic rays provide just enough energy to keep the cloud alive and chemically active for tens of millions of years, allowing it to form a richer array of molecules and ultimately to form stars at a more measured and regulated pace. They are the reason these cold nurseries are long-lived dynamic entities, not short-lived static ones. This creates a beautiful and profound symbiotic relationship between the most extreme energies the galaxy can produce and the coldest, most tranquil places it contains. The cosmic rays, born in searing heat and unimaginable violence, cannot be studied easily in empty space. They are invisible until they interact with something. They need the cold, dense matter of the molecular clouds to reveal their effects, to show us the intricate chemistry they catalyze. Conversely, the cold clouds, for all their internal dynamics, would be far less chemically rich and structurally sustained without this external bombardment. They require the high-energy particles to ionize their gases and maintain the delicate balance against gravity. Each extreme needs the other to create the dynamic, molecule-rich, star-forming environments we observe. It's a partnership that stretches across light years and energy scales, a collaboration between the fiercely hot and the profoundly cold that together fuel the strange and wonderful activity that makes our galaxy such a creatively fertile place. Yet for all their apparent emptiness, these voids are far from structureless. They are integral components of the largest scale architecture in the universe, the cosmic web. Picture an impossibly vast sponge, with galaxies and galaxy clusters clustered along its dense filaments and walls. The voids are the great bubbles within that sponge, the immense empty spaces between the threads. Their existence is not accidental. They are a fundamental prediction of our models of cosmic evolution, the natural outcome of gravity pulling matter into dense knots and leaving behind these expansive, underdense regions. The voids themselves have a structure. They can be vast spherical expanses or more irregular, elongated volumes, and they often appear to be arranged in a pattern themselves, with smaller voids merging into larger ones over cosmic time. This grand architecture means that when we talk about the emptiness of a void, we are not talking about a featureless nothingness, but a carefully sculpted and essential part of the universe's overall design. A negative space that gives form and meaning to the bright knots of the cosmic web. Perhaps the most tantalizing mystery hidden within these cold voids is the potential solution to the problem of the missing baryons. Astronomers have a very good census of the normal matter, the protons and neutrons that make up stars, galaxies, and us, that existed in the very early universe from measurements of the cosmic microwave background. But when they add up all the normal matter they can see in the present-day universe in stars, gas, and dust, a significant fraction, up to half, seems to be missing. The leading hypothesis is that this missing material is hiding in the voids, in the form of a tenuous million-degree gas known as the warm-hot intergalactic medium, or WIM. This gas is so hot that it emits very little light and so diffuse that it's nearly invisible to our telescopes. It is the ghostly, faintly glowing atmosphere of the cosmic web, and its primary residence is in these vast, empty regions. Detecting it is one of the greatest observational challenges in modern cosmology, requiring us to look for the subtle absorption signatures it imprints on the light of extremely distant quasars as that light passes through billions of light-years of void space. The profound cold of the void's background is the stage upon which this faint, hot whisper plays out, a reminder that emptiness is often an illusion, a trick of perception and technological limitation. The dominant process within these realms is one of almost unimaginable patience, the gradual cooling of the sparse gas through the weak, inefficient glow of radiation. An atom might become excited by a rare collision or a photon from a distant galaxy, and then, over a timescale that could span millions of years, it will slowly release that energy as a single, faint photon of light, radiating its minuscule amount of heat into the expansion of space itself. This is a universe operating in slow motion, where the timescales for change are not measured in years or millennia, but in fractions of the age of the universe itself. Gravity, the great architect of structure, is still at work here, but its influence is weak and diffuse. It acts not to collapse the void, but to slowly evacuate it even further, gently pulling the scant remaining matter toward the denser filament walls that border the void, a glacial river of material flowing over billions of years toward the glittering cities of galaxies. This imperceptibly slow motion is a form of activity, a purposeful shaping, proving that even in the deepest quiet, the universe is never truly at rest. This forces us to radically redefine what we mean by activity. We are naturally drawn to the spectacular and the violent, the supernova explosions, the colliding galaxies, the blazing quasars. But the void teaches us that activity has a spectrum, and on its far end lies a realm where change is so gradual and subtle that it is indistinguishable from stillness to any observer bound by a human lifespan. The void is active in its gravitational influence. its sheer volume dictating the expansion rate of the universe on the largest scales. It is active in its role as a reservoir for the missing matter that completes our cosmic inventory. It is active in the slow, atomic processes that play out over eons. Its profound cold is not a sign of death, but a different expression of life, a different mode of being for the universe. It is the deep, steady breath between the frantic heartbeats of stellar creation and destruction, and in that breath, the cosmos carries out some of its most patient and enduring work, reminding us that sometimes the most powerful forces are the ones that work in silence. But the truly mind-bending leap is considering that this quantum weirdness might not be confined to earthly labs or even familiar matter. Some of the most speculative and thrilling theories in modern cosmology propose that Bose-Einstein condensates could form naturally on a truly staggering scale in the coldest corners of the cosmos, potentially involving the most mysterious substance we know of, dark matter. Imagine a type of dark matter particle that is exceptionally light, not a heavy, sluggish wimp, but something more like an action or even an ultra-light scalar particle. In the cold, dense confines of a galactic dark matter halo, where gravity has drawn vast amounts of this material together, these countless light particles could theoretically lose their individual identities and merge into a single, galaxy-sized Bose-Einstein condensate. This wouldn't be a condensate in a magnetic trap. It would be a condensate shaped by its own gravity, a coherent quantum wave function on a scale of tens of thousands of light years. The implications of such a state are profound. A superfluid-like dark matter halo could exhibit properties that solve some of the most persistent puzzles in astronomy, particularly the strange dynamics of dwarf galaxies and the detailed structure of galactic rotation curves, which have long challenged the standard cold dark matter model. This idea posits that the invisible scaffolding of the entire universe might be governed not by simple particle interactions, but by a macroscopic quantum state born from extreme cold. The potential for such exotic states isn't limited to the dark sector. Within the incredibly dense and complex interiors of neutron stars, another possibility emerges. The core of a neutron star is a physics frontier where densities exceed that of an atomic nucleus, and matter exists in forms we can scarcely imagine. Among the theoretical phases proposed is a pion condensate or a kaon condensate, states where these subatomic mesons, which are bosons, undergo a phase transition into a Bose-Einstein condensate. This would fundamentally alter the properties of the neutron star's interior, making it softer or more compressible, which would in turn affect the star's maximum possible mass and its behavior during collisions. The recent observations of gravitational waves from neutron star mergers provide a new way to probe these extreme conditions. The tidal deformability of the stars as they spiral inward is exquisitely sensitive to the stiffness of the matter within them. A softer interior, potentially indicative of a condensate phase, would leave a distinct signature in the gravitational wave signal, offering astronomers an indirect way to test these wild theories. The cold within a neutron star is not a temperature we would recognize. It's a degeneracy cold, where pressure comes from quantum mechanical rules rather than thermal motion, creating the perfect environment for such quantum collective phenomena to emerge. If these condensates do exist in space, their effects would be anything but subtle. A cosmic Bose-Einstein condensate would represent a new, fifth state of matter operating on a scale that dwarfs human imagination, capable of influencing the dynamics of entire galaxies. One of the most dramatic manifestations could be in the form of coherent emission. Just as atoms in a lab BC can release light in a synchronized burst, a vast astrophysical condensate might generate powerful, coordinated emissions of energy that could explain certain types of unexplained transient signals or even contribute to the large-scale magnetic fields that permeate galaxies. Furthermore, the frictionless flow of a superfluid condensate could allow for the effortless transfer of angular momentum across vast distances, solving long-standing mysteries about why the outer regions of galaxies rotate at speeds that seem disconnected from the visible matter within. This isn't just a minor tweak to our understanding. It's a paradigm shift that suggests the coldest, most seemingly inert regions of space are actually humming with coordinated quantum activity, where billions upon billions of particles act as one single entity, their collective behavior shaping the evolution of the largest structures in the universe. The search for evidence of this is driving some of the most advanced theoretical work in astrophysics today, as scientists run sophisticated simulations to predict the observable fingerprints of such a state, hoping that the next generation of telescopes might finally catch a glimpse of this quantum ghost in the cosmic machine. Yet within this deep cosmic freeze, we find one of the universe's most captivating contradictions: the sudden, explosive release of energy in places where everything should be locked in permanent stillness. It seems to defy all logic. How can environments just a few degrees above absolute zero, where atomic motion is nearly halted, become the source of some of the most intense and brilliant outbursts we observe? The answer lies not in the cold itself, but in what the cold has perfectly preserved. These regions act as nature's ultimate storage lockers, safeguarding immense reserves of potential energy in various forms: chemical, gravitational, or even nuclear, waiting for the slightest trigger to unleash it in a spectacular display. Consider the strange phenomenon of cosmic mazes. In the cold, dark hearts of molecular clouds, molecules like methanol can absorb faint background radiation and store that energy. Under normal conditions, this energy would be quickly dissipated through collisions, but in the extreme cold, those collisions are so infrequent that the energy remains stored within the molecules. Then, when a passing shockwave from a forming star or even a subtle gravitational nudge disturbs the cloud, it creates a population inversion, a condition where more molecules are in a high-energy state than a low one. This triggers a chain reaction, not of light amplification like a laser, but of microwave emission, a maser. The result is an incredibly bright, highly focused beam of microwave radiation that can outshine the entire output of our sun at those wavelengths, all originating from a cloud colder than any place on Earth. It's a perfect example of how cold doesn't prevent energy release. It enables its storage and concentrates its eventual eruption. This principle of stored energy extends to the icy bodies wandering through our solar system. Comets, those ancient relics from the outer darkness, are often described as dirty snowballs, but that simple term belies their dynamic nature. As a comet approaches the inner solar system on its long, elliptical orbit, the sun's warmth begins to vaporize the ices on its surface, not just water, but frozen carbon monoxide, carbon dioxide, and methane. This process, called sublimation, is what creates the beautiful coma and tails we see. But sometimes the release of these volatiles is not a gentle, steady flow. Pockets of highly volatile ices, buried beneath the surface, can be sealed under a layer of less volatile material, like water ice or dust. As the sun's heat slowly penetrates this crust, pressure builds beneath it until it reaches a breaking point, resulting in a violent, jet-like outburst that can dramatically increase the comet's brightness in a matter of hours. The extreme cold of deep space has kept these volatile ices pristine for billions of years, and the slight warming of sunlight is all it takes to unlock their pent-up energy in a sudden, spectacular eruption. The same paradoxical relationship between cold and cataclysm can occur on a much larger scale with icy moons. A moon like Saturn's Enceladus has a surface of pristine, bright ice, reflecting sunlight and maintaining its deep freeze. Yet beneath that icy shell, tidal forces generated by Saturn's gravity flex and heat the moon's core, maintaining a global liquid water ocean. This internal heat seeks escape, and it finds it through cracks in the ice at the moon's south pole, where it erupts in magnificent plumes of water vapor and ice crystals that shoot hundreds of kilometers into space. The cold surface is not a barrier to this activity, it is a necessary part of the system. The icy crust acts as a containment lid, allowing pressure to build until it is forcefully released through these cryovolcanic vents. The contrast couldn't be more striking, a surface colder than any Antarctic night, giving way to geysers that testify to a warm, energetic, and potentially habitable interior. Even the seemingly placid Oort Cloud, that distant reservoir of frozen comets, is a testament to this paradox. Its inhabitants are in a state of gravitational suspense, orbiting slowly in the deep freeze. But a slight gravitational nudge from a passing star or a galactic tide can perturb one of these icy worlds, sending it on a long fall inward toward the sun. This gravitational potential energy, stored over eons in its distant orbit, is gradually converted into kinetic energy as it accelerates. By the time it reaches the inner solar system, it is moving at tremendous speeds, and its subsequent interaction with sunlight transforms it from a dormant ice ball into a brilliant, active comet. The energy for this stunning display was always there, stored in its position in the galaxy's gravitational field. The cold simply preserved the object until the universe was ready to release that energy on a grand stage. This recurring theme across the cosmos forces us to abandon the simplistic idea that cold equals inertness. Instead, we must see these frigid environments as capacitors, devices that store energy with incredible efficiency, often for immense spans of time, only to discharge it suddenly and dramatically when the conditions are just right. The cold is the perfect conservator, slowing down all processes to a near halt and preventing energy from dissipating wastefully. It allows for the accumulation of immense potential, whether in the form of chemical bonds, pressurized volatiles, or gravitational position. The resulting outbursts are not violations of physical law, but rather their ultimate expression, demonstrating that the universe's most breathtaking acts of release are often preceded by its most patient and profound acts of storage in the deepest cold. This incredible interplay between cold matter and light fundamentally transforms how we explore the universe, turning the very darkness of space into a brilliant source of information. To our eyes, a dense molecular cloud appears as a stark black silhouette against the Milky Way, a seemingly empty void. But this obscurity is an illusion, a trick of perception. The tiny dust grains and icy mantles within these frigid regions are exceptionally efficient at absorbing the shorter wavelengths of visible light, blocking our view of the stars behind them. Yet, this same material behaves completely differently when we observe it at longer wavelengths. Those microscopic dust particles, chilled to just a few degrees above absolute zero, absorb minuscule amounts of thermal energy from their surroundings and re-radiate it not as visible light, but as a faint glow in the far infrared and submillimeter parts of the spectrum. What our eyes register as a profound emptiness is, to a specialized telescope like the Atacama Large Millimeter Array or the James Webb Space Telescope, a blazingly bright structure, shining with the heat signature of its own cold contents. This is the great astronomical paradox. The coldest places in the cosmos often shine the brightest, but only if you know how and where to look. This shift in perspective, from optical blindness to infrared sight, is what allows us to peer directly into the heart of these stellar nurseries and witness the hidden processes at work. By tuning our instruments to these specific wavelengths, we can effectively see the dust itself, mapping its distribution and temperature in stunning detail, revealing the intricate filamentary structures that serve as the birthplaces for stars. Even more remarkably, the molecules that freeze onto these dust grains don't just sit there silently. They constantly vibrate and rotate, and each type of molecule does so at very specific energies, which correspond to unique frequencies of light. When we point a radio telescope toward a cold cloud, we can detect the faint whispers of these molecular vibrations. Each molecule has its own spectral fingerprint, a set of specific absorption or emission lines that act as a definitive chemical barcode. This is how we can confidently say that a cloud light years away contains ethyl formate, the molecule that gives raspberries their scent, or vinyl alcohol, or even glycine, the simplest amino acid. The cold environment is essential for this detection. It sharpens these spectral lines, making them narrow and distinct, allowing astronomers to identify a breathtakingly complex chemical inventory that would be completely blurred and lost in the thermal noise of a warmer environment. The light that passes through these cold clouds doesn't just get absorbed, it also gets imprinted with subtle clues about the physical conditions within. The pervasive chill itself can cause a subtle broadening of these spectral lines. This occurs because the molecules are moving, albeit slowly, and their motion causes a slight shift in the frequency of the light they emit or absorb due to the Doppler effect. By measuring the precise width of a spectral line, scientists can estimate the temperature of the gas, as warmer gas would have faster-moving molecules and broader lines. Furthermore, the intense gravitational pull within a dense, cold core can actually stretch the light escaping from it, causing a gravitational redshift that provides a direct measure of the core's mass and density. It's a form of cosmic forensics where light acts as both a messenger and a witness, carrying encoded details about the temperature, pressure, density, and velocity of the material it has traveled through. By carefully decoding these subtle distortions, we can measure the weight of a star-forming cloud, gauge the strength of its internal motions, and even predict whether it's on the verge of collapsing to form new solar systems. This entire field of study, this art of reading the universe in light that human eyes cannot see, transforms our understanding of the cosmos's darkest corners. We are no longer staring into an abyss. We are reading a dynamic and information-rich story written in the language of cold chemistry and physics. The obscurity is not a void but a veil, and by learning to see through it with the right technological eyes, we uncover a universe teeming with activity. Every dark patch in the sky becomes a potential window into the formation of molecules that are the very precursors to life, the birth cries of new stars, and the gentle, persistent dynamics that shape galaxies over eons. The cold, therefore, is not a barrier to observation but its greatest enabler, a natural filter that quiets the thermal chaos and allows the faint, precise signals of creation to shine through, proving that the most valuable secrets are often hidden in plain sight, waiting for us to learn how to see the light within the darkness. And if we truly want to understand the potential for life in these cosmic deep freezes, we need look no further than our own planet. Earth is home to organisms that don't just survive in the cold, they thrive in it, flourishing in conditions we once thought were utterly uninhabitable. In the permanently frozen soils of Antarctica, microbes known as psychrophiles make their homes within tiny veins of liquid water between ice crystals, metabolizing at a glacial pace. At the bottom of our deepest oceans, entire ecosystems cluster around hydrothermal vents, not reliant on the sun's energy at all, but on chemical energy from the planet's interior. These extremophiles are a powerful proof of concept, demonstrating that life is not a delicate flower requiring a perfect, warm climate. It is a tenacious force capable of adapting to and exploiting even the most challenging environments. This radically expands our definition of what a habitable world can be, pushing the boundaries of the traditional Goldilocks zone out into the frigid outskirts of star systems and into the hidden oceans of icy moons. The key isn't a specific temperature range, but the presence of three fundamental ingredients: liquid water, a source of energy, and the right chemistry. And as we've seen, the coldest places in the cosmos are often incredibly adept at providing all three. This opens the door to possibilities that sound like science fiction, but are grounded in solid biochemistry. On a frigid world like Saturn's moon Titan, where surface temperatures hover around -180 degrees Celsius, water is frozen solid, as hard as rock. But rivers and lakes of liquid methane and ethane flow across its surface. Could a form of life exist there, using liquid hydrocarbons as its solvent instead of water? It's a tantalizing thought. Such life would have to be built on a completely different biochemical foundation, perhaps using lipids for cell membranes and engaging in metabolic processes orders of magnitude slower than anything on Earth to account for the profound cold. The energy for such a system might not come from sunlight, but from the chemical energy released when acetylene and hydrogen react on Titan's surface, a reaction we know occurs there. While entirely hypothetical, this line of thinking forces us to abandon our water-centric, Earth-biased view of biology and consider that the universe, in its infinite creativity, might have invented life in multiple ways, with the cold not as a barrier, but as the essential condition for an entirely new tree of life to take root. The strange and dynamic activity we've been exploring in these cold realms is what creates and sustains the very niches where life could gain a foothold. Cryovolcanism isn't just a geological curiosity, it's a potential delivery system constantly churning and renewing the surface of a world, bringing fresh material and energy from a warm, liquid interior up into the cold outer shell. This process could efficiently circulate the essential building blocks for life, mixing nutrients and providing the kind of energy gradients that organisms on Earth exploit. Furthermore, the complex organic chemistry we see occurring on the icy dust grains of molecular clouds and within the comets of the Oort Cloud shows that the universe is not just making the simple stuff. It is pre-packaging and distributing a sophisticated toolkit of probiotic molecules, amino acids, sugars, and nucleobases, the very Lego bricks from which life is assembled. When a comet carrying this rich inventory crashes into a young, icy world with a subsurface ocean, it isn't just delivering water, it's delivering the potential for life itself, seeding that dark, cold abyss with the chemical precursors needed to get started. This realization injects a profound urgency into the exploration of these chilly worlds. Missions are no longer just about mapping geology or analyzing atmospheres. They are actively hunting for biosignatures, chemical indicators of biological processes. The Europa Clipper mission, for example, will fly through the plumes erupting from Jupiter's moon Europa, its instruments tuned to sniff out complex organic molecules and even potential cellular material. Similarly, concepts for a Titan Dragonfly mission envision a drone-like rotorcraft flying to different sites on that hazy moon, sampling its organic rich sands to look for any signs of chemical disequilibrium that might hint at metabolism. We are no longer simply asking if we are alone. We are methodically searching the most promising real estate in our solar system, guided by the understanding that the cold, dark places might be the universe's preferred nurseries for life. The frigid realms of space, once written off as barren and inert, are now at the absolute forefront of astrobiology, reminding us that life may not be a rare cosmic accident, but a natural and inevitable outcome of physics and chemistry, with the deepest cold often providing the perfect, quiet cradle for its emergence. To truly grasp the bizarre events unfolding in the cosmos's coldest corners, we cannot rely on observation alone. The extreme conditions there, the near absolute zero temperatures, the mind-bending quantum effects, the complex chemistry on dust grains, are often impossible to replicate in any laboratory on Earth. This is where the power of theoretical modeling becomes our greatest tool, a digital laboratory where we can recreate the universe's deep freeze and experiment with the very laws of physics. Scientists construct immensely complex simulations that weave together the intricate threads of quantum mechanics, fluid dynamics, magnetic field theory, and sophisticated chemical networks. These aren't simple animations. They are vast mathematical universes running on some of the world's most powerful supercomputers, allowing us to fast forward through millions of years of cosmic evolution to see what emerges from the cold. These digital experiments frequently yield results that are as surprising as they are enlightening. A model might show that a seemingly stable, cold molecular cloud on the verge of collapse is actually being held in a delicate balance by its own internal turbulence and magnetic fields, explaining why star formation isn't as efficient as we once thought. Another simulation might reveal how a slight nudge in temperature, just a few degrees, can trigger a rapid, cascading phase transition in interstellar ice, causing an amorphous, porous structure to suddenly crystallize and release a burst of trapped gases that jump-starts a wave of complex organic chemistry. These aha moments in the simulation aren't just academic curiosities. They are crucial predictions that send astronomers back to their telescopes with a new set of questions and a sharper eye for detail. This beautiful dialogue between prediction and observation is supercharged by a new generation of space and ground-based observatories. When a simulation predicts a specific molecular signature should be present in a particular type of cold cloud, astronomers can point the immense radio wave collecting dishes of the Atacama Large Millimeter Array toward that region of space. The data it returns acts as a verdict, either confirming the model's prediction or sending the theorists back to their code to refine their equations. Similarly, the James Webb Space Telescope, with its unparalleled infrared vision, can peer into the heart of these dark nurseries and see the very ices and chemicals the models describe, providing a ground truth that is more detailed than ever before. This iterative process of simulate, observe, and refine is how we move from simply cataloging strange phenomena to truly understanding the underlying why. The ultimate goal of this theoretical work is not just to explain what we already see, but to boldly predict what we should be looking for. The concept of superfluid helium in the cores of neutron stars didn't emerge from a single observation. It was a theoretical solution to the puzzle of pulsar glitches, an idea born in equations that later found supporting evidence in real data. The same is true for the behavior of dark matter in cold galactic halos, or the possibility of quantum tunneling driving chemistry in molecular clouds. The models provide a roadmap for discovery, pointing our most powerful instruments toward the most promising corners of the cosmos and telling us what to expect when we get there. They allow us to explore realms that are otherwise inaccessible, from the first microseconds after the Big Bang to the interior of a distant exoplanet, pushing the boundaries of our cosmic worldview and ensuring that our journey into the cold continues to reveal a universe that is stranger, more dynamic, and more wonderfully mysterious than we ever could have imagined. But our quest to understand the cosmos's coldest corners doesn't end with observations from afar. It is accelerating into a new era of direct, targeted exploration. A powerful fleet of next-generation missions, both underway and on the drawing board, is being purpose-built to venture into these deep freezes and answer the very questions we've been exploring. These aren't mere flybys. They are sophisticated robotic laboratories designed to analyze the strange activity of these frigid realms with instruments of unprecedented sensitivity, turning speculation into fact and mystery into understanding. At the forefront of this charge is the Europa Clipper, a mission that feels like it was pulled from the pages of a science fiction novel. Its target is Jupiter's icy moon Europa, a world with a surface colder than any Antarctic winter, yet one that hides a global liquid water ocean beneath its frozen shell. The Clipper won't land. Instead, it will perform a series of close flybys, using its suite of 9 dedicated instruments to act as a remote sensing powerhouse. Its radar will penetrate the ice, gauging the thickness of the crust and searching for those potential pockets of shallow water. A thermal imager will scan for recent eruptions of warmer ice, pinpointing active cryovolcanic sites. Most tantalizing of all, its mass spectrometers are designed to fly through the moon's watery plumes, directly sampling and analyzing the composition of the ejected material. This is the Holy Grail, a mission that will taste the ocean of another world without ever touching down, searching within that spray for the complex organic molecules and chemical imbalances that could indicate Europa's ocean is not just liquid but alive. While the Clipper explores within our solar system, the James Webb Space Telescope acts as our unparalleled eye on the cold universe beyond. Perched at a stable point in space, its massive golden mirror is tuned to see the cosmos in infrared light, the very wavelength at which cold objects shine brightest. JWST is already revolutionizing our understanding of cold places. It can analyze the chemical fingerprints of ices on distant trans-Neptunian objects in our own solar system, identifying different types of frozen molecules with ease. Looking far beyond, it peers into the hearts of dark molecular clouds light years away, deciphering the complex cocktail of organics freezing onto dust grains in stellar nurseries. It can even study the atmospheres of cold exoplanets, those frozen super-Earths and ice giants, determining their composition and weather patterns. Webb provides the context, showing us that the processes we see beginning in our own solar system are part of a universal tapestry of cold chemistry and physics playing out across the galaxy. The ambition doesn't stop there. Concepts for even more daring missions are in active development. Imagine a robot lander equipped with a heated drill, melting its way through the miles-thick ice of Europa or Saturn's moon Enceladus to release a free-swimming underwater drone into the alien ocean below. This is the goal of projects like the NASA-funded Scientific Exploration Subsurface Access Mechanism for Europa. This audacious technology would finally answer the question of what thrives in those sunless, abyssal depths. For the even more distant, frozen worlds of the Kuiper Belt, missions are being planned to orbit and map them in high definition, studying their bizarre geological activity and unique ice compositions up close, much like New Horizons did for Pluto, but with the ability to stay and study for years rather than a fleeting flyby. Each piece of data beamed back from these missions will be more than just a new discovery. It will be a critical test for our theoretical models. The predictions made in supercomputer simulations about quantum tunneling in chemistry or the behavior of superfluid ices will finally face the ultimate jury, direct observation. This iterative process of prediction and validation is how we move from guesswork to genuine knowledge, refining our understanding of fundamental physics and planetary science with every new byte of data. We are on the cusp of a great leap forward, transitioning from simply wondering about the mysteries of the cosmic deep freeze to actively probing them with tools powerful enough to reveal their secrets. This isn't just exploration for the sake of discovery. It is a deliberate, focused campaign to understand our origins and our place in a universe where the coldest, darkest places hold the keys to the greatest questions. Yet as we stand in awe of these scientific triumphs, we are inevitably drawn into a deeper, more personal reflection on what these discoveries mean for us, not just as observers of the cosmos, but as participants within it. The profound cold of space and the bizarre physics it reveals acts as a mirror, forcing us to confront fundamental questions about our own place in the grand scheme of existence. For centuries, humanity has often viewed the universe through a lens of comfortable familiarity, assuming the laws of physics we discern on Earth are universal constants and that our position is somehow central or special. The icy depths of the Boomerang Nebula, the quantum chaos within a dark cloud, and the hidden oceans of frozen moons deliver a powerful and humbling correction to this perspective. They present us with a universe that operates on rules far stranger and more magnificent than our everyday experience could ever suggest. A reality where matter can exist in multiple places at once, where friction disappears, and where life might blossom in sunless, frigid abysses. This isn't just an expansion of our scientific knowledge. It is a fundamental expansion of what we believe is possible, challenging the very foundations of our understanding and inviting a necessary and profound humility. This humility is not about diminishing our achievements, but about contextualizing them within a cosmos of near infinite scope and complexity. To learn that the water in our bodies, the carbon in our cells, and the very atoms that make us who we are were forged in the hearts of long-dead stars and assembled on icy dust grains in the dark void, is to understand that we are not merely living on a planet, but are an inseparable part of a vast, interconnected cosmic process. We are the universe itself becoming conscious, able to look back upon its own workings with wonder and curiosity. The cold cosmos, in all its silent, mysterious grandeur, teaches us that we belong to this universe in the most intimate way possible, yet it also reminds us that we are but a fleeting, momentary expression of its creativity. This realization fosters a deep sense of connection and responsibility, a cosmic kinship with all that exists, from the simplest hydrogen molecule in a distant nebula to the potential alien microbe swimming in a moon's hidden sea. It shifts our perspective from one of conquest and domination to one of participation and stewardship, urging us to explore not just with technological prowess, but with reverence and a commitment to preserving the wonder we are only beginning to comprehend. Ultimately, the journey into the cosmic cold is more than a scientific expedition. It is a philosophical and ethical pilgrimage. It compels us to reconsider the nature of reality itself, suggesting that our perception is limited to a narrow band of experience, and that true understanding requires us to embrace paradox, probability, and mystery. As we push the boundaries of knowledge, we are also forced to define the boundaries of our action. The discovery of potentially habitable icy worlds immediately raises profound ethical questions. If we find life on Europa, do we have a right to interact with it or even to sample it? What obligations do we have to protect these pristine environments from contamination? Our forays into these realms must be guided not merely by curiosity, but by a wisdom that acknowledges the potential impact of our presence and the profound value of what we might find. The silent, frozen vaults of space hold up a mirror to our own nature, asking us who we are and who we aspire to be as a species venturing out into the great, dark, and wondrous unknown. The answers we forge will define not only the future of our exploration but the very legacy of humanity as we take our next tentative steps into the cosmic ocean, forever changed by the chilling and beautiful truths we encounter in the deep freeze. From the ghostly outflow of the Boomerang Nebula to the hidden, churning oceans of icy moons and the complex chemical factories within dark molecular clouds, our journey has revealed a truth that defies all intuition. The coldest places in the cosmos are not the silent, empty voids we once imagined, but are instead the universe's most dynamic and creative workshops. In these profound deep freezes where atoms slow to a near standstill, the ordinary rules of physics recede, allowing the bizarre and the quantum to take center stage. We've witnessed how superfluidity might course through the hearts of neutron stars, how quantum tunneling unlocks chemistry in places too cold for traditional reactions, and how icy dust grains act as tiny laboratories assembling the very building blocks of life. This vibrant activity, hidden beneath a facade of absolute stillness, shows us that the cosmos reserves its greatest wonders for those who know how to look beyond the glare of starlight and into the beautiful darkness. These environments are far more than just barren wastelands. They are fundamental to the story of everything. They are the cradles where stars are born from the collapse of frigid gas, the protective vaults that preserve the pristine ingredients of planetary systems, and the testing grounds for physics that we can scarcely replicate on Earth. Each discovery we make in these frigid frontiers, from the detection of complex organic molecules in a cloud that smells of raspberries to the observation of water plumes erupting from a world of ice, peels back another layer of cosmic mystery. It reveals a universe that is infinitely more intricate, more interconnected, and more ingeniously strange than we could have ever dreamed just a generation ago. The exploration of the cosmic cold is, in essence, the exploration of possibility itself, a journey to understand the deepest laws of nature and our own place within this magnificent, unfolding story. This journey is far from over. With every passing year, new telescopes peer deeper into these frozen realms, and new missions are proposed to touch the ice of distant worlds. The questions we ask today will fuel the discoveries of tomorrow, and each answer will undoubtedly bring a dozen new mysteries to light. We want to hear which of these cold cosmic wonders captivates you the most. Does your imagination drift to the potential life swimming in the dark oceans of Enceladus, or are you drawn to the quantum weirdness of a Bose-Einstein condensate potentially spanning an entire galaxy? Share your thoughts in the comments below. We absolutely love reading them and discovering what sparks your curiosity about this incredible universe we all share. If this journey into the deep freeze has expanded your view of the cosmos, do us a favor and hit that like button, subscribe to the channel, and ring the notification bell so you won't miss our next exploration. Where should we go next? The heart of a black hole, the dawn of time itself? Let us know. Thank you so much for watching, and as always, wherever